Hello everyone, I welcome you all onto this channel and my name is Vinay Kumar from the Gate Mechanical team of PW, and this video series is basically a single shot video series for mathematics of course, and in this video we are going to take in a single shot for the complete linear algebra, which is one very important module for Gate mathematics, and also for it actually consists of some 2 to 3 marks every year. So we straight away start to this course, linear algebra, which many of you might be familiar with some different name, which is also called matrices. So many of you might have studied a bit of this with the name of this subject as, or the name of this particular module as linear algebra. Now this medium of teaching will be in English, and nowadays English is basically the language of the education, and 80% of the books across the world are written in English. And I'm telling you one thing, even if you secure a good admission in some IITs or IISc Bangalore in India, at least you will experience all of your professors almost will teach you in English. So I suggest you basically to have the understanding of the things in English, and definitely this will definitely help you out. Okay, so straight away going to this chapter where you use this linear algebra. If you ask this question to yourself, many instances you will be solving simultaneous equations, correct? Let us suppose if I give you this equation like a11x plus b11y is equal to c1, and a21x plus b21y is equal to c2. For example, let us suppose if I ask you to solve these two equations, it's very simple for you, right? You have a lot of techniques for you like elimination, substitution, you have a lot of techniques. But let us suppose if I try to increase the complexity, for example, instead of giving this 2D system, let us suppose I have given you system like this: a12x, or you can say y, plus a13z is equal to c1, a21x plus a22y plus a23z is equal to c2, and a31x plus a32y plus a33 you can say z is equal to c3. So let us suppose if I give you this particular system, it's a 3 equations with 3 unknowns, then you can still solve this system using such kind of techniques, but it's not very simple, correct? Now let us suppose if you get 4 by 4, then it's much difficult case. So basically matrices is the main application of this is you can solve simultaneous systems, and there are n number of applications in technical subjects. For example, many of you might have seen this matrix like I was talking, tau xy, tau yx and sigma yy. This is basically a 2D stress tensor. If you see in strength of materials or fluid mechanics, you get such systems. Similarly, if you're dealing with finite element analysis, you'll be getting stiffness matrices, all these things. Okay, so it has large number of applications, and linear algebra is definitely one very good subject to deal with all such things in mathematics. And myself, when I was doing some research earlier, I have dealt with a system of 101 unknowns and 101 equations also, because you see generally many things change with respect to time, location, temperature, there are certain things. So I was able to solve 101 by 101 system using matrices again, and of course with the help of some coding. But right now my aim is to tell you that at least linear algebra is one very important tool to crack all the such simultaneous systems in engineering. Okay, so let us straight away start from this basics, and this video will definitely help you out in understanding from the definition of a matrix, then slowly progressing to the advanced levels, such that you can clear your all the exams basically, and also a very good knowledge in matrices. Clear? So this video is helpful even for some JEE aspirants as well, if you try to go for the first 2 hours of this video. It's a single shot video on this complete linear algebra, and I'm very privileged to give you this information in a quick go before GATE examination. Okay, so now let us straight away start with the definition of a matrix. So what is a matrix? What is a matrix? For example, if you see, many of you feel that any rectangular array of elements is called a matrix, correct? In some books you find this definition: a rectangular arrangement of elements in rows and columns is called a matrix. But you have seen square matrices also. Then square matrix is not a rectangular arrangement, it's basically a square arrangement. So here I generally define this as any arrangement, or you can write any array, or you can say arrangement of elements in horizontal lines, and you call this horizontal lines as rows and vertical lines. you call these vertical lines basically as columns is called a matrix, is called a matrix. Now for example, if I'll definitely give one examples for each of the cases what we discussed, so that it will make you better in understanding the things. So examples, if I take, for example, I can take, normally these matrices are generally, you can write, generally matrices are defined by or denoted by, you can say generally matrices are denoted by uppercase letters. Okay, are denoted by uppercase letters, means basically capital letters. Okay, so uppercase alphabets, you can say generally uppercase alphabets. Okay, so for example, if I say A is equal to, if I write these elements, India, you can write, then what is the other 5-letter country? Okay, you can say Japan, for example. So if you see this matrix, then here all these elements I, N, D, I, A, again J, A, P, A, and all these elements are arranged in some horizontal and also in vertical rows. So basically this row is called the first row and this row is called the second row. And similarly, if you see, this column is called the first column. Similarly, this column is the second column. This is the third, similarly followed by this fourth, and finally you have this fifth column. So this is your fifth column. So if you see this example, this matrix capital A has 2 rows and 5 columns in it. So what we say, there is something called size or order of the matrix. Okay, so next we are going to, for that definition, size or order of the matrix. Size or order of the matrix. Now basically, if you want to see the size of a matrix, then the size is defined by number of horizontal rows you have and also number of vertical rows, I mean basically the vertical lines, basically the columns you have. Okay, so if a matrix has, if a matrix capital A has m rows and n columns, then it is denoted by A m by n. So basically this is read as A m by n, and if you see, this m is basically number of rows that you have, and this n is basically number of columns that you have here. Okay, now how we define matrices? Let us suppose I write a matrix, for example. Okay, so general notation of matrix, for example, if I write this matrix, A is equal to 2, 3, 4, for example, 3, 4, 5 and 4, 5, 6, for example. Let us suppose there is some matrix like this. Now many times in GATE examinations or in generally in some standard textbooks or advanced textbooks, you find the notation of this matrix in a different way. Means they tell about the same matrix but in a different sense. How? Look, I'll tell you. Basically what they give you is, for example, if you take this matrix is equivalent as A is equal to Aij for all 1 less than or equal to I less than or equal to 3, 1 less than or equal to j less than or equal to 3, and Aij is equal to I plus j. So what is the meaning of this sentence? How this matrix and this matrix both are same basically here. So if you see, normally if they denote Aij, this first subscript means basically I denotes row number. Okay, so this I denotes row number and j denotes column number. Okay, so this j denotes column number. So once if you want to specify location of any element in a matrix, let us suppose if I want to specify this element, then you know this element is in the second row and it's also in the second column. So basically if I denotes the row number and j denotes the column number, then I can say this element 4 which I have highlighted here is nothing but a22, which means it belongs to the second row second column element. Okay, so similarly if I want to spot about this 4 for example here, then this 4 is in the third row and first column, so we call this as a31. okay, similarly any other row, for example if we take this 5, this is in the second row third column, so we take as a23, and this element is given by some function of I comma j in general. okay, it can be I plus j, I into j, whatever, any algebraic expression they can put, sin I, whatever they want they can put. But if they want to generate a matrix, my intention is to tell you that they need not completely specify the matrix in this form, but rather they can specify you in this form. And here if you see, I value is less than 1, I is greater than 1 and less than 3. So basically if you see, I can take the values of 1, 2 and 3, which means this matrix A which you are talking about has 3 rows, and at the same time 1 less than or equal to j less than or equal to 3. That means this matrix can have 3 columns. So basically it's a 3 by 3 matrix. How do I know it's a 3 by 3? Because row numbers are from 1 to 3 and also column numbers are from 1 to 3. And how do I know what are the elements inside this matrix? That is given by this. For example, if I want the element a11, then aij is given as I plus j. So I value is 1, j value is also 1. So this 1 plus 1 is equal to 2. Similarly if I want, and if you see the first element is 2 in the first row. For example, if you want this element, it's a third row second column element. So third row second column element. So this is 3 plus 2 and this value has to be 5. So if you see, this element is 5 actually here. So that's how you actually need not completely specify the matrix. Okay, so this is one very important way which they ask you questions in examinations, and they actually define this size with the help of this inequalities, and they define the elements using some function in terms of I and j. So that's how this is one very important notation of matrices. Clear? And because I'm going to use this from now onwards, so that's how I'm going basically. Now I would like to give you some basic types of matrices, because these types of matrices means there are certain types of matrices like upper triangular, lower triangular, diagonal matrix, all these things, and these type of matrices, they have certain special properties in determinants, in inverse, in eigenvalues, all these things. Okay, so we will see slowly in this video how we progress. Okay, so types of matrices. I'll quickly put a heading: types of matrices. Types of matrices. Now the first type of matrix that I'm going to give you is upper triangular matrix. Upper triangular matrix. Upper triangular matrix. So what is this upper triangular matrix? So basically if you take any square matrix, then these elements for which I value is equal to j, so 2, 4, 6, because if you take this first element, this is a11, then this element is a22, this element is a33. So basically if you take this diagonal, for example, let me show using a dotted line. If you take this diagonal, then all the elements on this diagonal have same number of I comma j. So that's why we say, since it looks like a diagonal, we say those elements are called principal diagonal elements. Okay, this is the main diagonal, so principal diagonal elements here. Clear? So if you see this upper triangular matrix, a matrix A is equal to aij, where 1 less than or equal to I comma j less than or equal to n. This is how generally you can write for square matrices. You can denote both I and j in a single inequality. Normally in previous case I have shown two different inequalities, like 1 less than or equal to I less than or equal to 3, then 1 less than or equal to j less than or equal to 3, but it need not be like that. Once it's a square matrix, you can directly denote it. Okay, so this matrix is said to be an upper triangular matrix, is said to be an upper triangular matrix, is said to be an upper triangular matrix if aij is equal to 0 for all I greater than j. So what is the meaning of this equation? Okay, I have written this element will become 0 whenever I is greater than j basically here. Now what does this equation tells you? This tells you that all the lower diagonal elements, all the lower diagonal elements are zeros. All the lower diagonal elements are zeros. Now how do you know this? Look, for example, let us suppose if I take this matrix. Let us suppose if I take this matrix, a 3 by 3 matrix, let us take A11, A12, A13, similarly A21, A22, A23 and A31, A32 and A33 for example. Okay, so now if you take this matrix, it's a 3 by 3 matrix. Now I'd like to tell something here. Look, if you take this principal diagonal again, if you take this principal diagonal, now you can observe one thing. If you take the elements above this principal diagonal, means basically the elements in this block, if you see the elements in this block for example, okay, so if you see the elements in this block, you can say for example, so if you take the elements in this block, then you can observe one thing, here, that this I number will be greater than j number definitely for all the elements. Okay, so all these elements which are below this principal diagonal are called the lower diagonal elements, and all the elements which are above this principal diagonal are called the upper diagonal elements. Okay, and now if you check this, if you see the lower diagonal elements, I number will be more than this j number for all the elements. Similarly, if you take the upper diagonal, I will be less than this j for all the elements. So whenever I am telling I is greater than j, it talks about these elements here. Okay, so these are the elements which are below this diagonal are the elements for which I value is actually greater than j. So if you want to call any matrix upper triangular, you know all your lower diagonal elements must be zeros, which means this element should be 0, this element should be 0, and also this element should be 0. And I don't bother about whether these elements being zeros or non-zeros, doesn't matter, but as long as all these lower diagonal elements are zeros, I call my matrix as an upper triangular matrix. I hope it's clear to you. So basically, if you take any element below the principal diagonal, you have your row number greater than the column number, and for the matrix to be called as an upper triangular matrix, all these lower diagonal elements should be definitely zeros. Clear? So now with this understanding, let us move to the second type of matrix, which is lower triangular matrix. Lower triangular matrix. Now by this time you might have definitely guessed what is the case. Okay, lower triangular matrix. Lower triangular matrix. Now what is a lower triangular matrix? Look, a matrix A is equal to Aij, where 1 less than or equal to I comma j less than or equal to n is said to be lower triangular matrix if Aij is equal to 0. Now you all can guess this. I am pausing here for a second, so you can write, you can give the condition. So where if Aij is equal to where I is less than j. Very good. So where I is less than j. So what is the meaning of this line? So if you see, all the upper diagonal elements are zeros. All the upper diagonal elements are zeros. All the upper diagonal elements are zeros. Okay, so now if you see this condition, example again as I have given you previously, let me give you here also. If you take a 3 by 3 matrix, for example, by this time you might have already understood A11, A12, A13, A21, A22, A23, A31, A32, A33. Now again if you take the diagonal, if you take this diagonal, this is the principal diagonal. So I told you, and you know that upper diagonal elements must be 0, and whenever diagonal elements on the upper diagonal, definitely this I value means row number is definitely less than the column number. So these elements, they must be definitely zeros. All these 3 elements, of course it's a 3 by 3, so we have only 3 elements, so all the upper diagonal elements in general should be zeros. Okay, so now with this understanding, let us try to define what is a diagonal matrix. Okay, so what is a diagonal matrix? 3 diagonal matrix. Okay, so let us see what is a diagonal matrix. So basically you all know that diagonal matrix is nothing but all the principal means every elements other than the principal diagonal elements, they should be zeros, correct? So how we define that in terms of this ij notations? Let us check here. So a matrix A is equal to A is equal to Aij for all 1 less than or equal to I comma j less than or equal to n is said to be a diagonal matrix, is said to be a diagonal matrix, is said to be a diagonal matrix if, now you know one thing, if the elements are above the principal diagonal, they must be definitely zeros. If the elements are below the principal diagonal also, they must be definitely zeros. So which means except the principal, means of course even principal diagonal elements can be 0, but you are very much sure about the upper diagonal and lower diagonal elements being 0. So if the elements are lying either on upper diagonal or lower diagonal, then definitely you know one thing, I is not equal to j, correct? Because in case of upper diagonal elements, if you see, I is less than j. In case of lower diagonal elements, I is greater than j, which means in both the cases I is actually not equal to j, correct? So is said to be a diagonal matrix if Aij is equal to 0 for all I not equal to j. So this is one very important matrix. Why I will tell, because there comes one very important concept in matrices which is called diagonalization, which we will see at the end hopefully. So if you see, this is the matrix. So example, A is equal to, if I take this matrix A11, A12, A13, A21, A22, A23 and A31, A32 and A33 for example. So let us suppose this is the case. Okay, so if this is the case, then you can understand one thing, this is the principal diagonal here again. So this is the principal diagonal. So now if you check, whenever the elements are not on the principal diagonal, then definitely those elements should be zeros, and if elements lie away from the principal diagonal, means if they are not on the principal diagonal, then this I and j will not be equal to any of these elements. So that's why this element should be 0, this should be 0, this element should also be 0, and obviously all these elements, they should be zeros. Clear? So and even the principal diagonal elements can also be zeros, but one thing that we need to make sure is all the non-principal diagonal elements, they must be definitely zeros. Clear? So this is a diagonal matrix, and there is one very really important concept when you talk about this diagonal matrices basically. Okay, and of course you know how to add two matrices or subtract two matrices basically. So straight away I'm going to talk about multiplication of matrices in the next part. Okay, so we have a lot of many more types of matrices, but for that you need to understand certain concepts like transpose, multiplication of matrices, those kind of things. So that's why we are talking about multiplication of matrices for a while. Okay, so we will go for one thing, which is multiplication of matrices. Multiplication of matrices. Matrix addition and matrix subtraction, since many of you are very familiar at this level, so I'm not going again to that, but multiplication of matrices is something which is very important, so we'll see here. Okay, so multiplication of matrices. So the first property that I would like to give you is, if two matrices A m by n and B p by q. What's the meaning of this? A is the matrix of size m by n, means it has m rows and n columns. B is the matrix of size p by q, means it has p rows and q columns. So if two matrices A m by n and B p by q are to be multiplied, then definitely if you see, this number of columns in the first matrix should be same as number of rows in the second matrix. So this n should be definitely equal to p. So why this happens? Because if you have a quick remembrance of how we do the matrix multiplication, you can easily understand this. Because, and how we multiply these two matrices, look, I'll tell you. Let us suppose you have A, B, C, D, E, F, and so this is a matrix basically of size 2 by 3. Then definitely you should have a matrix starting with 3 rows and any columns you can have. For example, say 2 columns. If you design this, then 3 by 2, so 3 rows and 2 columns. So F, so let us say 1, 2, 3, 4, 5, 6, for example. Okay, so if you see, these two are equal, number of columns here and number of rows here, which I have stated. So how you do this multiplication basically? So if you see, the final output matrix is going to be of this size. Okay, so the final matrix, if you see, is going to be of this size. This is of the form m by q, so 2 by 2. Okay, so if you see, if you multiply these two matrices, for example, let us suppose if n is equal to p, and if you multiply these two matrices, the product matrix is going to have this order of m by q. Okay, so that's how here it's starting with 2, these two are equal, and finally it's ending with 2, so you have 2 by 2 here. Clear? Now let us see how we'll multiply. So you multiply this first element with this first element, means basically to get the first element here, then you should multiply the first row with the first column. Similarly, you will be having one more element here. So to get this element, since it is 2 1, a 2 1, so that's why you need to multiply this second row with the first column. That's how you get the first row of this matrix. I am repeating, if you want this element, for example, you know this is the element in the first or second column. So if you want the first or second column element in the product matrix, you need to multiply the first row with the second column. Okay, so anyhow, let us do the multiplication quickly. And so if you do the multiplication, a into 1, so a, plus b into 3, so 3b, plus c into 5, so 5c. So this is the first row, first column element of this matrix. Now what about the first or second column? So if you want first or second column, a into 2, so basically 2a, plus 4b, plus 6c. This is going to be the first row, second column. Okay, next coming here, second row, first column, so 2 1, here is 2 1, so d plus 3 times of e plus 5 times of f. Similarly here you can write easily 2d plus 4e plus 6f. Okay, many of you may feel that this is all basic stuff, but I'm repeating, understanding these matrices in this IJ formats is really important, so that's why I'm going for this. Okay, now I'll ask you one very important question. I'll give you time for 5 seconds. You can pause the video here and you can try to answer. Let us suppose if I want to multiply these two matrices, a is of size m by n and b is of size, let's say, n by q. P and n both are equal. So let us suppose if these two are same, then if you want to multiply these two matrices, what are the total number of multiplications you need to do? Look, for example, to get this first element, what I'm doing, I am multiplying this a with this 1. So first multiplication I'm doing. Again, to get this 3b, I am multiplying this b with 3. So I'm doing one more multiplication. C with 5, I'm doing one more multiplication. So basically, how many multiplications I need to do if you have this matrix of n and p basically here? Okay, the answer is number of multiplications required. Number of multiplications required to multiply two matrices a m by n and b n by p is, do you know how many? The answer is going to be m into n into p. So these many multiplications actually you need to do to get these elements. Okay, and this is, I can show you this result very easily. Okay, but before showing the result, I would like to give you one more important point. Number of additions required, number of additions required to multiply two matrices, two matrices A m by n and B n by p is you can see is m times of n minus 1 into p. So basically, how did I get these expressions? It is very simple. And first of all, you may have one doubt with the second point. If I am multiplying two matrices, how come additions are coming into the picture? Correct? This may be common intuition. But here, if you see, to add these three numbers, three multiplied values you have, but to add these three multiplied values, you are doing two additions. Correct? If you have three numbers, you will do two additions, right, to get the total sum. That's how. So let us quickly see how we are getting these formulas. For example, let us suppose A is equal to m by n matrix. So A11, A12, A13 and so on, A1n, because it has n columns, so there should be n numbers in the first row. Similarly, A21, A22, A23 and so on, A2n, and this goes on. Finally, you know that there are m rows in this matrix, so AM1. So you can see that this is AM1, AM2, AM3 and so on. Finally, you have ANN. This is the matrix that's going to come here. And what about this B matrix? B is, it has again n rows. So let us suppose you write B11, B12, B13 and so on. It has p columns, so you have written n by p, so this is B1p. Similarly, B21, B22, B23 and so on, B2p. So this goes on, and finally we have this n rows here, so that's why n2, n3 and so on, bnp. So these are the two matrices. Now let us suppose, if I ask you, if you want to multiply these two matrices, how many multiplications you need? First of all, tell me one thing. If you multiply these matrices A and B, the order of this matrix is going to be m by p. Correct? So because if you see, this is of order m by n and this is of order n by p, and if you multiply these two, the resultant is going to be having of order m into p. Now try to understand one thing. So total number of elements in this matrix will be m into p. You know this, correct? So total number of elements in this matrix is nothing but number of rows into number of columns. Now tell me one thing. If you want to get the first column element, what you will do? You will multiply this first row with this first column, correct? So for multiplying this first row with this first column, how many multiplications you will do? A11 into B11, first multiplication you will do. Next, A12 into B21, second multiplication you will do. A13 into B31, so third multiplication you will do, and so on. If you keep on doing, by the time you reach A1n into Bn1, you are total doing n multiplications, because the n elements in the first row, correct? Which means for getting the first column element, you are actually doing n multiplications, correct? So for getting one element, you are doing n multiplications. So to calculate this m into p elements, how many multiplications you will do? N into this mp, which is nothing but this mnp. Clear? Now you can understand the same thing. If you are doing n multiplications to get this first number, then how many additions you will be doing? Obviously number of additions are 1 less than the number of multiplications. So that's why if you are doing n multiplications to get this first column element, that means you will definitely do n minus 1 additions to add them up. So for one element you are doing n minus 1 additions. So for m into p elements, how many additions you will do? N minus 1 into mp. So this m into n minus 1 into p, otherwise you see, is the number of additions required to multiply the two matrices. That's basically in the multiplication. Okay, so this is one very important understanding from here. Now the second point that I would like to talk about matrix multiplication is matrix multiplication need not be commutative. Need not be commutative. So what is the meaning of this? You know the commutative law in mathematics. So basically means a into b, ab, you can say, need not be equal to ba. AB need not be equal to BA. Now, how I can show this? For example, because I have told some a rule just now that matrix multiplication need not be commutative. But how do I prove this to you? Look, I can prove you. For example, let us suppose you have taken this matrix. Let A is equal to, let A is of size 3 by 2 and B is of size 2 by 4, for example. Then if you see these two matrices, A into B is possible, correct? Means if you multiply this B with this A, this means this implies AB exists. Yes or no? AB will exist. Why? Because if you multiply in this order, this number of columns in the first matrix is same as number of rows in the second matrix. But B into A, if you try multiplying B into A, then 2 by 4 and 3 by 2 matrix, correct? So basically BA is something like this. B is 2 by 4 matrix and A is 3 by 2 matrix. So here clearly you can understand one thing, that here the number of columns and number of rows are not equal. Okay, so that's why this kind of multiplication is not possible for the same two matrices. So but BA doesn't exist. This doesn't exist. So forget about equating them or not equating them. Sometimes even if AB exists, BA may not even exist. Okay, so that's why you can never confirmly say that matrix multiplication is commutative. This this result is actually one good thing that shows that matrix multiplication cannot be commutative. Clear? So this is one very important property again. Now third property, matrix multiplication is associative. Matrix multiplication is associative. So basically what's the meaning of this? If you have three matrices, for example, let us say, then if you first, of course all these three matrices are facilitating matrix multiplication, means number of columns in the first matrix should be same as number of rows in the second matrix. All these things are holding good. So whenever in such cases, if you have three matrices, for example, then A of this BC will be same as AB of C. Means first of all, when you have three matrices, now if first you multiply BC and then you multiply A to the result, or if you multiply AB and then if you multiply C, the result remains same. Why this property is very important? Actually, frankly speaking, this property is very important. Why? I'll tell you. Let us suppose you got some big matrices, some 50 by 50, 100 or 50 by 100 and some 100 by 50 again, some matrices like this. Now many of you might be doing this C++ or C coding in general in labs. So what it happens is, normally you write a code. If you want to multiply three matrices, you will write a code, and the time of execution of this code depend upon the number of calculations, number of arithmetic calculations the computer perform, correct? Now let me give you one basic problem you can easily understand. Let us suppose you have this matrices. A is 3 by 4, B is 4 by 2, C is 2 by 3, for example. Let us suppose, so that the total product is going to be a 3 by 3 matrix, correct? So if you calculate this A, B, C somehow, then you are going to get a 3 by 3 matrix. Now let us see the two ways. For example, so let us suppose in the first case you are multiplying this A to this BC, and in the second case you are multiplying this AB to C. In both the cases you will get ABC, and both these values are also same. The computer displays the same values. But if you want to calculate number of operations performed by this computer, then let us check here. So this is equal to this BC. BC is a matrix of size 4 by 3. But what are the total number of multiplications required to calculate this product BC? Number of multiplications required is how many? 4m and p, correct? So 4 to the 8, 8 is a 24. So to calculate this product BC, you need 24 multiplications here, and of course 4 into 1 into 3, 12 additions also. Now this A is a matrix of size 3 by 4, and this BC is a matrix of size 4 by 3. Now if you multiply these two matrices again, how many multiplications you need? 3 into 4, 12, 12 is a 36. So plus 36 more multiplications you need, and total you need 60 multiplications to calculate this product A into BC, correct? So basically to calculate this product BC first, you need 24 multiplications. Once you get BC, to multiply this A with BC, you need 36 more multiplications. So total 60 multiplications. Come to this case. So if you calculate AB, for example, for calculating AB, how many multiplications you need? 3 4s are 12, 12 2s are 24. So 24 multiplications you need, and this matrix is a matrix of size 3 by 2, and C is a matrix of size 2 by 3, correct? So now if you see the multiplication of this AB with C, how many excess multiplications you need? This is a 3 by 2 and this is a 2 by 3. So 3 2s are 6, 6 3s are 18. So if you see, this is 18, so total 42. So here in this case you need only 42 multiplications. Of course, these are small numbers, so that's why 42 and 60, of course, still there is much variation. But imagine when you are dealing with 100 by 50 of that size, when you are in some research or some work, you will definitely write the programming in such a way, because you see the result is same in both the cases. So in such cases, what you write, you will definitely write the code in such a way that the minimum number of operations will be done by the computer, so that your execution time will be faster. So using this simple manual analysis, you will come to know which order to multiply, and you will write the code accordingly for reducing your execution time. Clear? So that's how in this case the number of multiplications required is less and it's minimum basically. Okay, so that's how this MNP is very important here, and of course this law, matrix multiplication is associative, is also very important. Clear? I hope I've cleared your questions. And previously when I was taking some YouTube class, people were asking me when you're going to give the content and all. Definitely, I know there's very less time for GATE 2023, so we have actually planned that if it's a single short videos, it would be very helpful for you, so that in a single go, some 4 to 5 hours if you spend, you will definitely get one complete module, some linear algebra, numerical methods, whatever, completely. Okay, so let's continue. Now, I would like to give you one very important property. In real numbers, let us suppose if you get some expression x into y is equal to 0, you write x is equal to 0 or y is equal to 0. Correct? Because in numbers, you know that for the product to be 0, at least one of them or maybe both can be 0. But in case of matrices, you can see the product of two non-zero matrices, can be a zero matrix. Look, this is very strange, correct? I will show you with the help of an example. Again, you can understand this. So let A is equal to some value A 0 0 0. So this matrix is not a zero matrix, because this A, small a, what I am taking here is non-zero. Okay, so small a not equal to 0. So definitely this matrix, you cannot call this a zero matrix. Basically, you cannot call this a null matrix, because this is non-zero. And B is equal to 0 0 0 B, and here also B not equal to 0. So here this is also non-zero matrix, correct? So these two are non-zero matrices because they have at least one element as non-zero. But if you calculate this AB, let us see what it turns out. A 0 0 0 into 0 0 0 B. So now if you calculate this, the outcome is going to be 2 by 2. A into 0 plus 0 into 0. This is 0. A into 0 plus 0 into B. This is 0. Since these two elements are zeros, definitely these two elements will also be zeros. So if you see, this is a null matrix. Okay, so this is null matrix. This is null matrix. So that's how you have seen clearly. These are two non-zero matrices, but still the result is a zero matrix, which generally don't happens in real numbers. So that's why this law, or you can say this, what do you say, this result, you can say this result is also one very important result, because generally you have this intuition that for the product to be 0, at least one of them should be 0, but in matrices you need not have that. Clear? Now let us continue the types of matrices. Or before continuing, I would like to give you one more point. Okay, so transpose of a matrix, this is one very important thing. Transpose of a matrix. Transpose of a matrix. So what is transpose of a matrix? So transpose, what's the meaning of this? Basically reflection. Okay, so if you interchange, you need to actually interchange them. So a matrix B is equal to Bij for all 1 less than or equal to I less than or equal to n, and 1 less than or equal to j less than or equal to m, is said to be transpose of a matrix, is said to be transpose of a matrix, capital A is equal to Aij for all 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n, if aij is equal to bji. So this is how you define transpose of a matrix. And normally in simple terms, you know, if you interchange rows and columns, then definitely you will get the transpose of the given matrix, correct? Now why this definition is very important, because if you see very soon after this single short videos, we'll come up with a problem solving series basically. So now if you see why this in that you'll see a lot of questions that transpose is given in these notations. Okay, so now if you see what is the meaning of this, let us try to understand. First of all, you need to understand one thing. This matrix capital B is of size n by m, correct? It's not m by n, it's n by m, because row numbers can go from 1 to n and column numbers can go from 1 to m. Similarly, this matrix A, which is the initial matrix, it has m by n order. So definitely you know one thing, when you have a matrix of order m by n, then if you interchange rows and columns, then the number of rows will become number of columns and the number of columns becomes number of rows. So this matrix B will be of this size, n by m, correct? For example, let us take some simple values, 2 and 3 let us take, then this becomes 3 by 2. For example, let me take one matrix. If I take this matrix 2 by 3, so 1 2 3 4 5 6, then you know, if you want to call this B as A transpose, which is denoted by this, so then you know you need to interchange rows and columns. So this first column can be interchanged as the first row, then second row and third row. So now if you see, this is of size 3 by 2 because this is of size 2 by 3. It's quite obvious, correct? Now what is the meaning of this matrix? Look, if I take Bij, means if I take for example B23 or B22 element, B22, then definitely this is going to be same as A22. Or if I take A13, then definitely it is going to be B31. So that's why I told you that Aij is equal to Bji, means if you are taking second or you can say first or third column element in B, you should take third or first column element. Okay, so these two will be equal. That's what I have defined in slightly complex terms, because this is generally important for GATE examination. Okay, and you can write one more statement. It is denoted as B is equal to A transpose, T on the superscript of T of A basically here. Okay, so that's why I hope you understood this. I'm repeating, whenever you are making a transpose, the order of the matrix gets interchanged. It means basically if this is of size m by n, then this becomes of size n by m, as you have seen. And obviously if you find out a element Aij, this element will be same as Bji with the order and row number reversed, because you have interchanged the matrices. That's the reason, and this is how you actually define the transpose of a matrix. And this is very interesting thing, because transpose means basically rows become columns and columns become rows. Normally if you see the meaning of transpose, this, if you have any matrix and if you do transpose of it, the points will actually come as a reflection about the line y equal to x basically. Okay, so for example, if you have 1 2 matrix, then if you transpose it, it becomes 2 1, and that point 1 2 and 2 1, if you take these 2 points, they are nothing but the reflection of each other about the line y is equal to x generally. Okay, so that's why this transpose is one very important operation in matrices. Now if you see properties of transpose, I would like to give some properties of transpose. Properties of transpose. Properties of transpose. Okay, so now the first property. Let us suppose if you transpose any matrix even number of times, for example, then you will get the same matrix, correct? Let us suppose if you transpose once, okay, then you will get the transpose of that matrix. Now let us suppose if you transpose it again, means if you apply the transpose 2 times, then what happens? First time when you do the transpose, you will get the interchange of the rows and columns, but second time when you are interchanging again, you will again get the original matrix. Okay, so even number of transformations give you the same matrix, odd number of transformations give you the the transpose matrix. Okay, so second, if k is any scalar, if k is any scalar, scalar means some number, okay, some constant. If k is any scalar, then ka whole transpose is actually equal to k times of A transpose. So this result is again very important because you can never transpose any scalar. Okay, so for example, if you see 2A, for example, if I take this matrix A is equal to 1 2 3 4, simply I'm just denoting it. So this implies if I calculate 3 times of A, I need to multiply 3 to all the elements. So if I do the 3A whole transpose, 3A whole transpose, this gives me 3 9 6 12. Correct. So this matrix is nothing but 3 times of 1 3 2 4, and this is 3 into this is A transpose. But scalars, these scalars, they never undergo any transformation basically. Okay, so that's what we have here. Then third, you can see some A plus or minus B whole transpose. If we have this, then this is equal to A transpose plus or minus B transpose. Means basically if you take plus here, here also it is plus. If you take minus here, this is also minus. You can check all this with simple examples. And one very important property that I'm going to give you now is AB whole transpose, or you can write C also whole transpose is equal to C transpose B transpose into A transpose. So all these are basically some nice results of addition multiplication of transposes of matrices. Okay, and this result is very important. Fourth result especially we'll use after some time in this lecture. So now if you see, this fourth one is a pretty much good property of matrices actually. And anyhow, these are the 4 important properties that generally sometimes they ask you in examinations and also in general university exams. Now coming to the continuing to the types of matrices, we have defined 3 types of matrices. What are they? Lower triangular, upper triangular, and also diagonal matrix. Correct. So let us continue. So again, fourth, if you see, we'll define something called scalar matrix. Scalar matrix. So in simple terms, if I want to explain you what is a scalar matrix, it's basically a diagonal matrix, but this time all the diagonal elements are equal. Like for example, you see the case of identity matrix, all the diagonal elements are equal. Okay, so that's how this scalar matrix is basically done. So a matrix A is equal to a matrix A is equal to Aij for all 1 less than or equal to I comma j less than or equal to n is said to be a scalar matrix, is said to be a scalar matrix if Aij is equal to some constant k for all I is equal to j and 0 for all I not equal to j. So you can see this time this Aij is given as some function of I comma j, but whenever I is equal to j, means if element is lying on the principal diagonal, then it should have some fixed value, but when elements are non-diagonal elements, then definitely they are zeros. And you can see this is something like this. Example, if I take 3 by 3, then you can see k0 0 0 k0 and 0 0 k. So this is how you can get a scalar matrix. Basically all the principal diagonal elements are same. You can write here a diagonal matrix, a diagonal matrix, a diagonal matrix with all the principal diagonal elements, with all the principal diagonal elements, with all the principal diagonal elements being same, with all the principal diagonal elements being same actually here. Okay, so now if you see, if you can understand one thing carefully, if k is equal to 1, then this matrix is called identity matrix. Correct? Because in an identity matrix you have the principal diagonal elements 1 and all other elements zeros. So when k is equal to 1, because this can be any constant, so when k is equal to 1, this matrix is called identity matrix. And if k is equal to 0, if k is equal to 0, this is called null matrix. Null matrix. Okay, so this k is equal to 0, this gives you null matrix actually here. Okay, so these are 2 special cases of this scalar matrix. So basically you deal with identity matrix everywhere when you talk about inverse of the matrix, orthogonal, all these cases. And null matrix is again the common what do you say, additive law, means basically if you see additive identity matrix is basically this case, means if you add any matrix to this matrix, null matrix, you will again get the same matrix. Okay, so this is scalar matrix. Now I'll go for one very important matrix which is called symmetric matrix. Symmetric matrix, you can tell by the name itself, the matrix is symmetric about its principal diagonal. So now you see what is a symmetric matrix. Okay, so in simple terms, you know, A is equal to A transpose. Let us write it in terms of Ij notations. A matrix A is equal to Aij, where 1 less than or equal to I comma j less than or equal to n, I comma j less than or equal to n, is said to be symmetric, if Aij is equal to Aji. Means, what does this mean actually here? If you see, this Aij is equal to Aji, means if you take any element symmetric about the basically symmetric about the principal diagonal, then the elements values are same. Okay, so example, I would like to give you example. A is equal to, for example, you can write 2 3 4, then this is also 3 4, 5 6, then this is also 6 7. Let us suppose if you take this, then what happens here? If you see carefully, this is the principal diagonal, so this is the principal diagonal. So if you see this element, for example, if you see this element is on the second row, the first row, second column. So that element 3 which I have rounded off is A12. So now this A12 will be same as, for example, if I write this A12, now if you interchange this Ji values, this should be equal to A21, correct? So if you see, this is also same here. So these two elements will be same generally. Similarly these two elements, similarly these two elements. So about the principal diagonal, if you take the corresponding reflection, then the reflection value and the actual value both will be same actually. Okay, so this is how you define a symmetric matrix, and in general you can write basically this A is equal to A transpose. Clear? So that's how, this is one very important thing in matrices. Now I would like to give you one very important type of matrix, skew symmetric matrix. Okay, this matrix is very much important. Okay, why? I'll talk about it when I come to the eigenvalues. Okay, so see here, 6 skew symmetric matrix. Skew symmetric matrix. So again, in simple terms, A is equal to minus A transpose, but let us write it in Ij notations. A matrix A is equal to Aij for all 1 less than or equal to I comma j less than or equal to n is said to be skew symmetric. Is said to be skew symmetric matrix if Aij is equal to minus Aji. So basically if you see, again here the reflection value should be same, but of course with a opposite sign. Okay, so numerically these both are same values in terms of magnitudes, but in terms of signs they are actually opposite. Example, I can tell you one thing. Example, you can get many examples. Example, A is equal to 0 0 0. If you write 2 here, then this is minus 2. If you write minus 3, then this is plus 3. If this is 4, then this is minus 4, and you can say like this. So here if you see, this is one example of a skew symmetric matrix. So for example, across the principal diagonal, this is the principal diagonal. So from this principal diagonal, if you take element A12, then this A12 and A21 means these two elements, if you see magnitude wise they are same, but there is a sign difference between them. Now you can understand one thing from this example itself, all the principal diagonal elements are zeros. Why this is happening? Look, I'll tell you. I'll give you some two nice points here. First point, principal diagonal elements, or you can write all the principal diagonal elements. All the principal diagonal elements of a skew symmetric matrix. Of a skew symmetric matrix are 0. All the diagonal elements of a skew-symmetric matrix are 0. Now why this is happening? Because in general, if for a skew-symmetric matrix, for a skew-symmetric matrix, as I have told you, Aij is equal to minus Aj. Now let us suppose if the diagonal, this element falls on the principal diagonal. Okay, so this element falls on the principal diagonal, means for I is equal to j, this Aii is equal to minus Aii. So this implies 2 times of Aii is equal to 0, which means your Aii should be equal to 0, means this element value should be equal to 0 whenever it falls on the principal diagonal, because obviously 2 is not 0. Okay, so here if you see, whenever element falls on the principal diagonal, the magnitudes wise they should be same, but signs it should be opposite. Okay, but these two, they denote the same values. Basically if I'm talking about 1 1, this is the only element, correct? So if you see, when I is equal to j, this principal diagonal element should be equal to the same principal diagonal element. So from this simple analysis, all these principal diagonal elements of a skew-symmetric matrix is 0. And second point I would like to give you here, the sum of all the elements, of a skew-symmetric matrix, the sum of all the elements of a skew-symmetric matrix is 0. Basically this is 0. Clear? If you see, because for every element that you find, there will definitely a element with a opposite sign, correct? So when you add these two, you'll get 0. Similarly, when you add these two, you'll get 0. When you add these two, you'll get 0. For every element that you find, you will definitely find a reflection with a opposite sign. So when you add these two elements, you'll get 0. So similarly, every total sum of this elements in this matrix turns out to be 0 here. Clear? Now I would like to give you one very important result coming up to this symmetric and skew symmetric matrix. Look what I'll tell you. Every square matrix can be decomposed, means splitting up, can be decomposed into sum of a symmetric oh, I'm sorry, I think it's space limitation, is sum of a symmetric and a skew symmetric matrix. A symmetric and a skew symmetric matrix. Now you see how it happens. Look, I'll tell you. So if you take any, basically what I'm telling you, if you take any square matrix, then this square matrix can be written as sum of a symmetric matrix and a skew symmetric matrix. Look how it happens. Can I write, if I take a square matrix A, this can be written as half times of A plus A transpose and half times of A minus A transpose. Can I write this? Because I can write this, because if you simplify the things, this plus A transpose by 2 and this minus A transpose by 2 and plus A transpose by 2, they cancel each other. So A by 2 plus A by 2 will again give you A. So now if you see this, if you see this matrix, this matrix is always symmetric, and this matrix is always skew symmetric. Now how come you know this? Because look, tell me one thing. Let us suppose if a matrix A is symmetric, for example. Okay, let us take some matrix B is symmetric. If B is symmetric, then any multiplication of B is also symmetric. Means basically if I take 3 times of B, 5 times of B, 10 times of B, whatever I take, 10B, 5B, 3B, whatever you take, all these are also symmetric matrices. Similarly, if B is skew symmetric, then again this 3B, 5B, 7B, all these things are, or 2B, 4B, anything, all these things are skew symmetric. So how to identify whether a given matrix is symmetric or a skew symmetric matrix? Look, I'll tell you. Let C is equal to A plus A transpose. Okay, So what does this imply? If you take C transpose, this gives you A plus A transpose whole transpose. So this is equal to, in properties of transpose I have given you, if you have sum of two matrices whole transpose, you can write the sum of individual transposes. So this is equal to A transpose plus A transpose whole transpose. So this is A transpose plus this is A, and this is again same as C, because C is same as A plus A transpose or A transpose plus A, both are same. So C transpose is finally ending up with C. So that's why this matrix C is actually symmetric. Okay, so this implies C transpose is equal to C. So this C matrix, what you assumed, A plus A transpose, is always symmetric. Similarly, if you take this D, let D is equal to A minus A transpose. So this implies your D transpose is equal to A minus A transpose whole transpose. So A transpose minus this A transpose whole transpose, if you write, then this is going to be A transpose minus A, and if you take a minus sign, this is coming out as A minus A transpose, which is nothing but minus D. So your D transpose is equal to minus D. So which means this implies that this matrix is skew symmetric. Okay, so this is symmetric matrix. So this is basically symmetric, and this A minus A transpose is always skew symmetric. Okay, so if you take any square matrix, you can definitely split this into sum of two matrices. Out of that, one is symmetric and the other being skew symmetric. Okay, so I hope we are clear with this result, that every square matrix can be split into sum of a symmetric and a skew symmetric matrix. Okay, now let us go for one very next important result, that normally these statements, when they ask you in examinations, people get very afraid, but they are simple. Look, if A comma B are symmetric matrices of same order, symmetric matrices of same order, symmetric matrices of same order, then I'll give you the result first, then I'll show you how it's happening. First is AB plus BA is always symmetric, AB minus BA is always skew symmetric, but provided these are symmetric matrices individually. Okay, so is always skew symmetric. Now how come this is possible? Look, I'll tell you. You need not actually remember these results, but you can actually show them. So firstly, they are given A and B are symmetric matrices. So given A transpose is equal to A and B transpose is equal to B. Now let us consider the first case, AB plus BA. Okay, so when you consider the first case, let us see what's happening here. So the first case is, let C is equal to AB plus BA. So whenever you want to check whether a matrix is symmetric or skew symmetric, just simply consider the transpose of it. C transpose is equal to AB plus BA whole transpose. So this is nothing but AB transpose plus BA transpose. Now I have told you the multiplication of matrices basically. So if you apply transpose of any multiplication, then the result is going to be like this: B transpose into A transpose plus A transpose into B transpose. So this is equal to, since these two are individually symmetric matrices, I can replace this B transpose with B and A transpose with A similarly here. So this is going out to be BA plus AB. Okay, so this result I can write as AB plus BA, which is again equal to C. So you have started by considering C transpose, and finally you ended up that C transpose is same as C. So this matrix AB plus BA is always symmetric. Here one caution: I have written BA plus AB as AB plus BA, not because that BA should be equal to AB. No, that's not the case. But since the summation is commutative in any way, so this is BA plus AB or AB plus BA, both give you same answer, but not this BA should be equal to this AB. This need not happen. Okay, so please be sure with this. Now second, let C is equal to, or D you can say, AB minus BA. then what this tells you, D transpose, if you take AB minus BA whole transpose, so this is AB transpose minus BA transpose, which is equal to B transpose A transpose minus A transpose into B transpose, because you have seen AB whole transpose is the transpose, individual transpose multiplication, but taken in a reverse order. So this is equal to BA minus AB. So if you take a minus sign here, you will get AB minus BA, which is nothing but minus D actually. So this ends with D transpose is equal to minus D. So definitely D is a skew symmetric matrix. And what is D we have taken? This AB minus BA. Okay, but this transposes we are able to replace in this form because it's individually given that both these are symmetric matrices. Clear? If this individual symmetricity is not given, then definitely you cannot substitute this B transpose as B, A transpose as A. Sometimes they'll give skew symmetric here, then again the process needs to be same, but in place of B transpose, let us suppose if they give A and B are skew symmetric matrices, then here you will put B transpose equal to minus B and A transpose is equal to minus A. Okay, so that's how we actually generate the results, and these two results are very much easy now. You need not remember them, actually they are very easy to derive or to show them. It's just some 2-3 basic properties. If you apply, you will get the answers. Clear? I hope I'm clear till this point. So this is a single short video, so by the completion of this video you will be able to get complete knowledge on this linear algebra, which is very very good for GATE examination. Okay, so and of course this video I'm inclined towards GATE syllabus, so that's why I'm dealing with this. Okay, now once you are with this, now I would like to give you some more properties. Okay, so now some more types of matrices let us give. So how many types I have given you till now? So all these are properties, 6 types I have given you. So let us go for the 7th type. So 7th, orthogonal matrix. Orthogonal matrix. So what is an orthogonal matrix? So let us see. A matrix capital A is said to be orthogonal, if A times A transpose is equal to A transpose times A, which is equal to identity matrix, okay, of same size of course. So A into A transpose, this A into A transpose is equal to A transpose into A is equal to I. Now let us see here. Okay, I hope mic is good. Yeah, mic is good, so no issue. So A into A transpose is equal to A transpose into A is equal to I. So let us take one example and let us see. Example: A is equal to, for example, say cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. So let us suppose this is some matrix. Now if you multiply this matrix with its transpose, so A into A transpose is equal to cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Now multiply the transpose of this matrix. So if you do the transpose, it's like cos theta sin theta 0 minus sin theta cos theta 0, 0, 0, 1. Now if you multiply these two matrices, you can easily understand that first column element, if you multiply this first row with this first column, cos theta into cos theta, cos square theta, plus minus sin theta into minus sin theta, sin square theta, plus this 0 into 0, 0. So the first column element is going to be cos square theta plus sin square theta. That's it. Okay. Now first second column element, cos theta into sin theta plus minus sin theta into cos theta. So this is cos theta sin theta minus sin theta cos theta, which is 0. Next, third row. So the first row with the third column, cos theta into 0 minus sin theta into 0, 0 into 1. So total 0. So this is how you have this. Next, second row first column, sin theta into cos theta plus cos theta into minus sin theta. So this is sin theta cos theta minus cos theta sin theta, and that gives you 0 directly. Now second column, sin theta into sin theta, sin square theta, plus cos theta into cos theta, cos square theta. So again you got here sin square theta plus cos square theta. Okay, next second or third column, again it is 0 directly. Now third or first column, these two are have zeros, 1 into 0, 0, this is also 0, and finally here you have 1 into 1, this is 1. So sin square theta plus cos square theta is always 1 irrespective of the theta value. So 0 1 0 and 0 0 1, which is actually an identity matrix. Now if you want more examples, you can do one thing. Whatever you can generate a matrix by putting different values of theta. Let us suppose if I put theta equal to 0, let theta is equal to 0, then I'll get one matrix that B is equal to cos 0 1, sin 0 0 0, this is 0, then this is 1, this is 0 0 0 1. So I'll get identity matrix, and identity matrix is again one one of the orthogonal matrix. If I put theta is equal to some 90 degrees for example, then you'll get 0 minus 1 0 1 0 0 0 0 1. That's again one more orthogonal matrix. So you can, if you want to generate n number of orthogonal matrices, you can just go for some n values of theta. Whatever the value of theta you put for this particular configuration, you always end up with an orthogonal matrix. Clear? So orthogonal matrix is that matrix which when you multiply with its transpose, you always get an identity matrix. Okay, and this example I hope it's clear to you. Let me have some water. Okay, so let's continue. So this is orthogonal matrix. Now I would like to give you one more important matrix, which is involutive matrix. Involutive matrix. Involutive matrix. So in this, if you see involutive matrix, a matrix capital A is said to be involutive if A square is equal to I, which means if you square any matrix, you will get the identity matrix of same order. And for getting this A need not be an identity matrix. There can be some different matrices, okay, where if you do A square, you will get I value. Let us see how you get this. Many times I'll be looking downwards because I have the system here. So if there is some issue with the mic, I'll get to know. Okay. Otherwise, this recording, it's not a live class, so I don't know what's happening. So anyhow, look here. A matrix capital A is said to be involutive if A square is equal to I. Let us see how we'll get this. I'll give you one simple example. A is equal to 4 minus 1. Let us keep. So if you keep 4 minus 1, then this is 15, and this is 2 times of this, so minus 4. So let us suppose if you take this example, it's a simple example for example. Okay, now if you calculate this square, 4 minus 1, 15 minus 4, and this 4 minus 1, 15 minus 4. So if you calculate this product, you can see 4 4s are 16 minus 1 into 15 is 16 minus 15, which is 1. So 4 into minus 1 is minus 4 plus minus 1 into minus 4 is plus 4. So minus 4 plus 4, this is 0. 15 4s are 60 plus minus 4 into 15 is minus 60. So 60 minus 60, again this is 0. 15 into minus 1 is minus 15 plus minus 4 into minus 4 is plus 16. So 16 minus 15, this is again 1. So if you see this matrix, this matrix is an basically involutive matrix. So I would like to give you one very good property here. Sometimes they give you that let A is an involutive matrix, and they give you some complicated elements inside, and they'll ask you for A inverse. Okay, so we'll talk about how to do in A inverse simply and all. But right now, if you see in this matrix, there is one very special property that A inverse is basically A inverse is basically equal to A. Okay, so what happens in that case is whenever you with all the difficulty when you try to calculate A inverse, finally you try to get the same matrix as the inverse matrix. Okay, and even after getting the same matrix, many of you will have this doubt that have I done some wrong calculation or what, I have got the same question matrix. But this is actually the case with this matrix. The inverse of this matrix will be same as the matrix itself. Okay, that's why if you observe, you can tell clearly, A square is equal to I is what you got, correct? So A into A is equal to I, but generally this I can also be written as A into A inverse, correct? So that's why if you compare generally these two matrices, they will be same, of course. Okay, so that's why this A inverse is equal to A in this case. Clear? So let us go for the next things. So this is involutory matrix. Now I will give you one again, some good matrix, which is idempotent matrix. Idempotent matrix. Okay, so what is this idempotent matrix? Look, I'll give you a matrix capital A is said to be idempotent matrix, is said to be idempotent matrix, idempotent matrix if A square is equal to A, if A square is equal to A here. Okay, so look, if A square is equal to A, now try to understand. So basically if you try to square any matrix, you will get the same matrix. Let us see, can we write any example here? Example, A is equal to, again let us take 4 minus 1 here for example. So if you take 4 minus 1, this any multiplication, for example 3 times you write, so 12 minus 3 for example. So if you take this matrix, okay, all these matrices, why I'm talking, because they have certain properties in determinants. Okay, so in determinants, if I say the determinant of an orthogonal matrix is plus or minus 1, you should know what is orthogonal matrix by that time. Okay, similarly if I talk something about determinant of an idempotent matrix, you should know what is idempotent matrix. So that's why these matrices I'm discussing now, and of course there are many gate questions on this types of matrices, okay, which you will come to know later in the PYQs solving sessions. So anyhow, let us come here. So 4 minus 1, 12 minus 3. So this implies, if you calculate A square, for example, 4 minus 1, 12 minus 3, and 4 minus 1, 12 minus 3. So if you multiply this, A square is going to be equal to 4 4s are 16 plus minus 1 into 12 minus 12. So 16 minus 12 is 4 again. So minus 4 plus 3, it's minus 1. 48 minus 36, 12 minus 12 plus 9 minus 3. So this is again equal to A. Okay, so this is how you get this matrix, which is this idempotent matrix actually here. Okay, because I will talk about some properties of this matrix again when I come to the determinants actually. Okay, so now let us go ahead, and I would like to discuss one last type of matrix before I go for the determinants actually. Okay, you have seen transpose of the matrix, how we need to identify whether the given matrices are symmetric matrices, geosymmetric matrices. We have seen all these things. Okay, now we'll go for one important topic, which is determinant. But before going for the determinant, we have one last type of matrix that of course we have many types, but in gate point of view, I would like to discuss one particular matrix at this point, which is actually a nilpotent matrix, you can say. Nilpotent matrix. So what is this nilpotent matrix? Let us see here. A non-zero matrix, capital A is said to be nilpotent matrix, if there exists a value n such that n belongs to z plus. Means basically what's the meaning of this? N is a positive integer. Okay, so n is a positive integer, and a power n is equal to a null matrix basically here. Okay, so means whenever you take any non-zero matrix but some value or some higher power of that matrix is a nilpotent matrix, then you call that matrix as a nilpotent matrix. Okay, now let me see what is the case. Example, A is equal to, so let us take 2 minus 1 and 4 minus 2 for example, let us say. Okay, fine, good enough. So 2 minus 1 and 4 minus 2 for example. If you take this just in check, so 2 times of this. Okay, fine, yeah, 2 minus 1 and 4 minus 2. Now if you calculate this A square, you see this is a non-zero matrix, but if you multiply this matrix to itself, 2 minus 1, I'm dealing in 2 by 2 so that calculations will be easy. The same can hold good for 3 by 3s also. 4 minus 2, so A square is equal to, now if you multiply 2 2s are 4 plus minus 1 into 4 is minus 4, so 4 minus 4 0, 2 into minus 1 minus 2 plus minus 1 into minus 2 is plus 2, so minus 2 plus 2 0, 4 2s are 8 plus minus 2 into 4 is minus 8, 0, 4 into minus 1 minus 4 plus minus 2 into minus 2 plus 4, which is again 0 here. So if you see, this A square is a null matrix, but actually A is not a null matrix. Okay, this is again in evidence to that result what I have given there, that product of two non-zero matrices can be still a zero matrix. Okay, so that's why you can see this is the case. And here I would like to add one more point, because you know, it's a good point. The least value of n, the least value of n for which this A power n is equal to this null matrix is called index of the nilpotent matrix. Index of the nilpotent matrix. Okay, so this is called index of the nilpotent matrix. Now try to understand one thing, because if A square is 0, then definitely from next onwards every power will go to 0. A cube, A power 4, A power 5, all these things will be zeros, because A cube can be written as A square into A. So A square is 0, A cube is also 0. So all this goes on, but 2 is the first time, this whenever this n is equal to 2, this is the first time when A power n became 0. So index of this matrix is actually 2. Clear? For some matrices you can have 3, 4, what can be the depending on the type of matrix, but here right now this is called this you know, nilpotent matrix basically, and this value, the least value of n for which this A power n turns out to be a null matrix for the first time, is called index of this nilpotent matrix. Okay, so with this we finish this first part of this video, like types of matrices and basic matrix algebra, multiplications, additions, or you can see some types of matrices, symmetric matrices, nilpotent, orthogonal, all these things. Okay, so now next we'll move on to the second part of this video, which is the talk about determinants. Okay, so let us go ahead and let us discuss the concept of determinants. Determinants or determinant, you can say. Now if I ask you, for example, if I ask you if this is a matrix, and if I ask you what is the determinant of this matrix, okay, so immediately you start telling AD minus BC, correct? A into D minus B into C. But if you observe the question carefully, I didn't ask you what is the value of the determinant, I asked you what is determinant, correct? So you should definitely know, because even this question, I'll tell you one of the experiences that I had recently, have you know appeared for BRC interview also. So now I'll tell you one thing, in every interviews, generally in technical interviews, there will be one faculty from or one you know, interviewer from maths, actually from mathematical background, and they'll try to ask you some questions. So you prepare a lot of things in mathematics and you go for the interview, but finally they ask you what is determinant, and you will end up with telling the value of the determinant. Okay, so that's why this understanding of the concept of determinant is actually very important. Okay, so now let us see what is this determinant actually. Look, I'll define the definition formally and then we'll see what's happening here. Okay, and you know, whenever you are trying to calculate a 3 by 3 determinant, you let first term minus second term plus third term, means between every terms you are actually alternating the plus minus sign. Why you are alternating this plus minus sign? Okay, we'll see all these things in this you know part. Look, so determinant, the sum of the sum of product of elements of a row or column of a matrix with their corresponding cofactors. So what are these cofactors and what is this definition? Basically product of sum of, there are different things, correct? So let us see what we are actually talking about. Okay, to make you understand this, I'll go with the help of a 3 by 3 matrix so that you will understand. Okay, so look here, let us suppose I have taken this matrix. Let A is equal to A11, A12, A13, A21, A22, A23, A31, A32 and A33. Actually, if I have explained it with the help of 2 by 2, you have actually got what is the definition of a minor or something, but anyhow, let me show you with this. Now, if I see this matrix, then there are total 9 elements. So now we write something called minor of A11, for example. Okay, so if I ask you about this minor of A11, then see, this is the element containing A11. So this is the column which is containing A11 and this is the row which is containing A11. So if you delete this row and column from this matrix, you will get some sub matrix. Sub matrix is basically some small part of the matrix. Okay, so from this matrix, if you delete this column and this row, then what happens here? You will end up with this value, that A22, A23, A32 and A33. So if you see, this value is nothing but A22, A33 minus A23, A32. You need to understand one thing here. I am directly going with the case of 3 by 3. That's why I am not explaining you why you need to multiply these two and then with a minus sign these two. Okay, if I have started with the example of 2 by 2, you might have easily understood, but again, I know that at this level you'll be knowing how to calculate the determinant of this. I'm just writing directly. Okay, but actually I should start the discussion with the 2 by 2 matrices, then you will come to know why I am multiplying this cross minus this. Okay, but right now I am assuming you know how to do this, so I'm doing it repeatedly. Now similarly, if I want to write minor of some other element, for example minor of A12, let us suppose I'm writing minor of A12. So if I want to write minor of A12, then this is the column and again this is the row that is containing A12. So this is left with, if I delete this column and this row, I have A21, A23, A31 and A33. So if you simplify this, A21, A33 minus A23, A31. Okay, next, why I'm doing, I want to write for 3 elements, minor of A13 also I'll write. Okay, so minor of A13 also I'll write. So now you see here, minor of A13, if I take this elements, this is the column containing A13 and this is the row containing A13. So if you delete this column and the first row, you will end up with thing like this. So determinant of A11, A21, A22, A31, A32. So this is equal to, if you do this again, A21, A32 minus A22 times A31. Okay, so this is how you have this. Now these are the 3 elements which I have written intentionally, but if you want, you can write for all the 9 elements. So if you write for all the 9 elements, you will get 9 different minors. Okay, so now let us see what I define by a cofactor. So cofactor of an element Aij, this is equal to minus 1 whole power I plus j times minor of aij, minor of aij. Now if you see the cofactor of a11, a12, all these things, you will get different elements with a plus sign, minus sign change. Now try to understand the definition. Now if you see, I can get, look, this is the first row. For example, I have calculated the minus of the first row, a11, a12, a13. So now try to understand one thing. If I calculate the minus, then definitely I can calculate the cofactors of these elements also, correct? So what will be the cofactor of this? This minus of a11 into minus 1 whole power 1 plus 1. Similarly, cofactor of a12 is equal to a12, I mean this minus of a12 into minus 1 whole power 1 plus 2 into minus 1 whole power 1 plus 3. Similarly here. Now try to understand one thing. If I want to calculate the determinant, det A can be written as, now look at this definition, the sum of, forget this sum of, first of all, product of elements of a row or column with their corresponding cofactors. Look, let us suppose if I take the first row, then what I should do is, I should multiply this a11 with the cofactor of this a11. Then I need to sum this to the product of this a12 with the cofactor of a12 plus a13 into cofactor of a13. Means basically if you see this, det A is equal to a11 into cofactor of a11 plus a12 into cofactor of a12 plus a13 into cofactor of a13. Look, here I have taken the first row, but it's not mandatory that you need to take always the first row. You can take second row, third row, anything, or you can also take first column, second column, third column, anything, but you need to multiply the same cofactor corresponding to that element. This must be done carefully. Okay, so now let us check here. This is equal to a11 into, now cofactor of this a11 will be nothing but minus 1 whole power 1 plus 1 into minor of this a11, correct? So minus 1 whole power 1 plus 1 into minor of a11. Let us suppose if I write this as m11, this is m12, this is m13 minus basically. Okay, so now you try to understand one thing, plus a12 into minus 1 whole power 1 plus 2 into m12 plus a13 into minus 1 whole power 1 plus 3 into m13. So now let us substitute the values. If you substitute the values, what you will get? a11 times of this minus 1 whole power 1 plus 1 is nothing but plus 1. So first of all, I want you make you understand that why you are putting a plus minus sign alternatively, because this gives you plus sign, this gives you minus sign. Again, this gives you plus sign. If you have 4 by 4 for example, then 1 plus 4 will give you a minus sign. That's the reason why plus and minus signs keep on alternating depending on this sum of minus 1 whole power, this 1 plus sum basically here. Okay, so if you see, depending on this summation, here you have a plus sign and here you will get a minus sign. Again, here you will get a plus sign, here you will get some minus sign. That's the reason of writing alternative plus and minus in case of determinants. Okay, so this, if you write this, that term a22 a33 a22 a33 minus a23 a32, then there is a minus sign here, so minus a12 times of this m12, which is which is basically a21 a33 a21 a33 minus a23 a31. Then again here you have a plus, so plus a13 times of, there you can write a21 a32 minus a22 a31. So basically this is how you actually write the determinant value when they ask you for the determinant of the given matrix. Okay, so anyhow, this is the determinant value. Now I would like to tell you one thing. If you multiply the cofactors of the same elements with the corresponding cofactors, you will get the determinant value. Means if you multiply these row elements with the corresponding cofactors, you will get determinant. Now let us suppose if you multiply the elements of a row with other row cofactors, means basically you are taking elements of one row and you are multiplying these row elements with cofactors of some other row, then what you will get the result? The answer is going to be 0. Okay, look, I will show you how it's coming. Basically how it's coming, I'll show you with the help of a 2 by 2. Look, let us suppose you have taken some 2 by 2 matrix which is A, B, C, D. Now if you write the minus, anyhow I would like to directly write the inverse of this. If you want to write the inverse, you should always write this 1 by determinant AD minus BC, and now interchange these two terms. So D and A comes here, and of course these two has to be replaced with a minus sign, minus B minus C. You will see shortly how this is coming and all. So A inverse, the simplest form to write A inverse is this 1 by AD minus BC. You write directly, then you swap these two, means basically you interchange these two diagonal terms. So D and A comes here, then you replace these two with a minus sign. Okay, so anyhow if you see, look, I will show you. If you take the first row, means M11 minor of first row first column element, if you take this element, then if you delete this row and this column, then D is the thing which is left over. So D M12. So if you take this element B, now if you delete this row and this column, you are left with this C. So this is C. Next M21. So if you take this C, for example, if you delete these two, you have a B, and M22 will be A. Correct? So what are the cofactors? So if you want to talk about cofactors, then cofactor of 1 1, you can write capital A11, cofactor of 1 1 is equal to 1 plus 1 into D, which is equal to D. Cofactor of 1 2 into this C, which is minus C. Cofactor of 1 3, okay, this is a 2 by 2. So 2 1 is equal to minus 1 whole power 2 plus 1 into B, which is minus B. A22 is equal to minus 1 whole power 2 plus 2 into A, which is equal to A. Okay, so these are the cofactors. Now this is the cofactor of 1 1 1, this is the cofactor of 1 2, this is cofactor of second or first column, this is cofactor of second or second column. Now as I told you, you all know that A, if I ask you this, you will directly tell me AD minus BC. But how this AD minus BC is coming? If you multiply first row with the corresponding cofactors, you will get, correct? So det A can be written as first row elements multiplied with the first row cofactors. So first row element A, what is the cofactor of A? You can see cofactor of first column element is D. Then plus second element B into what is the cofactor of this first or second column element? Minus C. So you can see this is nothing but AD minus BC, which is the determinant of this matrix. Next, you can calculate det A using another method also, by taking some other also. For example, let us suppose if I take using this column BD, any column you can take, BD let us take. So first B into, then what is the cofactor corresponding to this B? Cofactor corresponding to this B, this is first or second column element. So first or second column is minus C, plus this element is D, and what is the cofactor corresponding to D? Last element is A. So you can see this is nothing but minus BC plus AD, which is nothing but AD minus BC. Again you will get the determinant. So my intention is basically to tell you that if you multiply elements of a row with their corresponding cofactors, or maybe column with their corresponding cofactors, you will get determinant value. Okay, now what happens if you multiply the cofactors of some other row with the actual some other elements? Okay, for example, let us try to multiply this row with these cofactors. If you try to multiply, let's see what happens. A into, so cofactor of C is how much? Minus B, plus B into, what is the cofactor of D? Cofactor of D is A. So if you see AB and minus AB, the answer is got to be 0. Okay, so if you multiply elements, means if you multiply elements of a row with other row cofactors, you end up with having a 0. This is a 2 by 2 case. It's very simple. So I have shown you using this 2 by 2 case, but actually you can show for 3 by 3 also. So basically my intention is to tell you that if you multiply elements, means basically if you take the sum of this product of elements with their corresponding cofactors, you will get the determinant, and if you multiply some other elements cofactors, you will get this 0. Now I want to tell you one thing here. Look, let a11, a12, a13, a21, a22, a23, a31, a32, a33 are cofactors of A. Are cofactors of A. Then what can I write? I can form some cofactor matrix, correct? So cofactor matrix is going to be something like this. Cofactor of the first column element, first or second column element, first or third column, a21, a22, a23, a31, a32 and a33. Okay, so let us suppose this is the cofactor matrix, means basically you have calculated cofactors of all the 9 elements. Now let us suppose if you take the transpose of this. Why I am taking transpose, you will come to know when I multiply. Okay, so let us suppose I am taking transpose. So transpose of cofactor matrix, transpose of this cofactor matrix is called adjoint matrix. Transpose of this cofactor matrix is called adjoint matrix. Now let us see, means basically if you want adjoint matrix, this is equal to cofactor matrix whole transpose. Okay, now let us see what is this adjoint matrix basically. So this implies adjoint matrix, or generally you write this as ADJ of A, adjoint of A. So adjoint matrix of A is nothing but this transpose of the cofactor matrix, which means A11, A12, A13. Similarly, A21, A22, A23, A31, A32, A33. Okay, so let us suppose this is the cofactor, this adjoint matrix. Now let us see what happens. I want to show you one very important result at this moment, because that result is the main basic for the concept of adjoint and inverse of the matrix actually. Okay, so let us see here. So considering A into adjoint of A, for example, if you consider this A into adjoint of A, look, I am considering this A11, A12, A13. These are normal elements, so matrix A elements, A31, A32 and A33. Now let us suppose if you multiply this with this adjoint matrix, which is A11, A21 or A12 and A13, because we have transposed it, A21, A22, A23, A31, A32 and A33, for example. So let us suppose if you have this. Okay, so once you have this, then see what's happening here. If you multiply these two, A into adjoint of A, into adjoint of A is equal to, look, try to observe carefully now. For getting the first column element, you need to multiply the first with the first column, and all this means if I write A22, that means this capital A22 is nothing but cofactor of this element small a22. If I write capital A32, this capital A32 is nothing but cofactor of the element small a32. Correct? Now let us see if you multiply. If you multiply this first with the first column, A11 into capital A11 means you are multiplying the element with its corresponding cofactor, plus A12 into capital A12 plus A13 into capital A13. So if you see, the first column element is nothing but the sum of product of elements of this row with its corresponding cofactors. So which means you are going to get determinant of A here. Correct? So the first element that you are going to get is actually the det A. Next, if you see first row with the second row cofactors, obviously 0. First row with the third row cofactors, this is 0. Next, second row with the first row cofactors 0, second row with second row cofactors, then again this is det A, second row with third row cofactors 0. Similarly this is 0 0 det A. So this is one very important thing, and from this matrix if you take this det A constant as multiplication, you will have det A times of 1 0 0 0 1 0 0 0 1, so which is nothing but det A into identity matrix. So if you take any square matrix, this result is very much important, that for any square matrix, A into adjoint of A into adjoint of A is equal to det A times of that matrix. Okay, so this is one very important equation, and this equation is coming here from the definition of determinant, because if you see here you are supposed to write det A only if you know the definition of det A, correct, because you are actually summing up the product of these elements with its corresponding cofactors, correct. So for writing this matrix here, you should know two conditions, that if you multiply elements of a row or column with its corresponding cofactors, you will get determinant, and if you multiply elements of a row or column with some other cofactors, you will get 0. So that's how these two rules will help you out in writing this matrix. Capitally, I mean this this determinant of A 0 0 0 det A 0 and 0 0 det A, and you were able to form this equation with the knowledge of definition of determinant. Okay, and why this equation is very important, because this is the equation that gives you a fundamental for the concept of inverse of a matrix. Okay, multiplicative inverse. If you say, look, if A inverse is multiplicative inverse of a matrix, then definitely you know that A into A inverse gives you identity matrix, correct. Now let us see how to calculate the inverse of this matrix. Look, I'll tell you. For this equation we have, look, we have A into adjoint of A is equal to det A into I. So if you multiply this A inverse on both sides, A inverse into A into adjoint A is equal to det A is anyhow constant into A inverse into I. Look, in matrices it is very important, if you are multiplying A inverse before this, here also you should multiply before this. Okay, this is one, because in numbers we don't follow this generally, but in matrices you have seen the order of multiplication is of very much importance. So that's why if you see, if you are multiplying this A inverse here, then definitely you should multiply A inverse before this I. Okay, so now we have seen matrix multiplication is associative basically, correct. So I can take multiplication of these two first and then these two. Now if you see, A inverse into A is nothing but I into adjoint A is equal to det A into A inverse, because A inverse into I is again A inverse. Identity matrix is just an identity, so if you multiply any matrix with identity, you will get the same matrix. So this gives you adjoint of A, and this is equal to det A into A inverse. So from this equation you will end up with one formula, that A inverse is equal to 1 by det A into adjoint of A, and this is the fundamental equation which is known to you from your basic schooling, but you never know what is why this equation is coming, and many times they tell you for A inverse to exist, this det A should not be equal to 0. This is the reason, this is how this is coming, and if this inverse has to exist, then definitely this det A should not be 0, because definition by 0 is not defined. So that's why this this for A inverse to exist, you can say for A inverse to exist, this det A should not be equal to 0. Clear? So this means if you see, we generally name this with some technical term. A must be non-singular. non-singular matrix, you can say. A must be non-singular matrix. Okay, so this capital A must be non-singular matrix. Okay, and what's the meaning of singularity? Basically, singularity means determinant is equal to 0 anyhow. Okay, and here I would like to add one more point. It is denoted as, you can say, it is denoted as, you can write here, it is denoted as a det A, or sometimes you write this det of A. Both are same, both they mean determinant is the actual thing that they are asking you for. Okay, so now if you see, fine, so this is the fundamental equation that A inverse is equal to 1 by det A times of adjoint A is one very important fundamental equation for calculating inverse of the matrices. Okay, so we have seen that this fundamental equation A into adjoint of A is equal to det A into I is the most fundamental equation that gives rise for this A inverse matrix. Now let us try to look at some properties of this determinants. Okay, so if you see properties of determinants, because this is one of the very important part where generally questions turn over in GATE examination. So properties of determinants. Now let us see certain properties. Okay, so if straight away first property you can write the determinant of an upper triangular, the determinant of A, you can write A here, and that's not the, oh, I think there is some issue, just a minute. Just a minute, so wait for the program to respond. So yeah, so I hope things are going fine, you are getting enough time to make your notes. I'm not coming up with a PPT because when I write you'll also have some time to make your own notes. Okay, and this video series definitely is going to get all the concepts of your maths in very less time. So hardly if you spend some 4 to 5 hours every day for some 7 to 8 days, let us say, you will be very clear to the mathematics portion. Okay, so that helps you in getting very good marks in GATE, obviously. So anyhow, let us try to continue here. So of a upper triangular matrix, or a lower triangular matrix, or a diagonal matrix, a diagonal matrix is the product of principal diagonal elements of the matrix. So this is one very, very important property. So principal diagonal elements of the matrix, okay, of the matrix. So this is one really very important property, because many times what they give you, they'll give you matrices of high orders, 4 by 4, 5 by 5 and all. So when they give you such orders, this normal procedure for writing the determinant will not work that effective. So in such cases you can use this property. So directly if you multiply the product of the principal diagonal elements, you will get the determinant value. So this first property is really some very good property in matrices. And second, I would like to give you if A is an n by n matrix, if A is a n by n matrix, then you can write first det of A transpose will be same as determinant of A. So basically if you calculate the determinant of a matrix or its transpose, both the values turns out to be the same thing. Okay, and second, k into A whole power n, or you can say det of Ka for any scalar k, det of Ka is equal to k power n times of this det A. Look, basically you might have known this property. Let us suppose if I have this determinant A11, A12, B11, or you can say A21, basically A21 and A22. Let us suppose if this is equal to determinant of A. Now let us suppose if I want to calculate determinant of one particular matrix, like for example det of k1 a11 k1 a12 means the first row elements are multiplied by a constant k1 and second row elements are multiplied by a constant k2. So in such case, if I want to calculate the determinant of this matrix, you can see this k1 can be taken out from this first row. So k1 can be taken out from this first row. Similarly, from this second row, you can take a k2 out. So k1 into k2 times of this det a11 a12 a21 a22 basically here. Okay, so now this a11 a12, this determinant of 2 by 2 is again nothing but k1 into k2 times of det a here. Okay, now if you see carefully, when a matrix is multiplied by a constant, what happens? This k1 k2 values will be same, correct? Because every element of the matrix is multiplied by some constant. So let us suppose if k1 is equal to k2, this becomes k square times det a, because it's a 2 by 2. So if the matrix is of order n by n, then definitely you will have k power n times of determinant of a. Okay, now we'll go for some other properties also. Third property, you can say the determinant of a matrix, the determinant of a matrix is 0 if one of its row, if all the elements in a row or column, if all the elements in a row or column are zeros basically. Okay, so let us suppose if you have a particular determinant in which one complete row is 0 or maybe one complete column is 0, then definitely if you take the product of cofactors with respect to that row, then you know obviously 0 into some cofactor of that element plus again 0 into something plus again 0 into something. So this total will give you a 0 value. That's the reason why in determinants, if one row or one column is completely 0, then the determinant value is going to be 0 here. Okay, now example, you can see I'll give you one example also better. So if you see determinant of this root 3 by 2 minus 1 by 2 0. Okay, so again pi by 4 2 by 8 or 2 by ln 2 0. Then again if you see for example some values, some random values, minus 1 by root 2. Okay, e power 4 0. So let us suppose if I give you some determinant like this, since this one complete column is 0, this determinant value is definitely 0 irrespective of these elements. So sometimes they can ask you these kind of things. Okay, so you should be little careful. And fourth property, you know, fourth property, if two rows or two columns, of a determinant are interchanged, if these are interchanged, then the determinant changes its sign. Then the determinant changes its sign. So basically what I am telling here is, let us suppose you have this determinant a11 a12 a13 a21 a22 a23, similarly a31 a32 and a33. So let us suppose if you have this determinant, now this determinant will be equal to the same determinant value when you swap two rows or two columns, there comes a minus sign. Means let us suppose if I swap second and third row for example, or second and third column, anything, I am swapping second and third row. So a11 a12 a13. Now this a21 a22 a23, instead of that I need to give the third row. So a31 a32 a33 and a21 a22 and a23. So if you take this determinant, the difference between these two determinants is nothing but we have swapped second and third rows. So in such cases the result changes with a minus sign actually. Okay, so this determinant value will be same as negative of this determinant value. Clear? So when you interchange two rows or two columns, the determinant changes its sign. This is again one very important property here. Now coming to the fifth, the value of a determinant of a matrix, the value of determinant of a matrix the value of determinant of a matrix, basically the value of determinant of a matrix is 0, or you can say remains unchanged, better. So yeah, remains unchanged, remains unchanged if remains unchanged if row or column transformations, row or column transformations, row or column transformations are performed on the matrix, are performed on the matrix, are performed on the matrix, are performed on the matrix. So basically what do I mean by this? Means let us suppose if I have this matrix or this determinant, for example, look, let us suppose if I take this determinant a11, a12, a13, a21, a22, a23, a31, a32 and a33. So this determinant value will be same as, let us suppose if you perform some row transformations, for example you have subtracted second row from first and added the third row. Let us suppose if you do any transformations, this determinant value doesn't change. Okay, so for example what I'm doing, for example what I'm doing here, example transformation what I'm doing is r1 changes to r1 minus r2 plus r3, let us say, for example. Okay, so we have done some row transformation. So this first row changes as first row minus second plus third. Okay, so which means first element is here is going to be a11 minus a12 plus a13. Next this element is going to be a12, sorry, I think here we have done some error, so a11 minus a21 plus a31. Okay, similarly here a12 minus a22 plus a23 plus a23. Okay, and next anyhow I'm writing this on the other side, so a23 or basically this is 32, so this is a, just a minute, yeah, so now let us continue, plus a 32, and third element, first or third column element will be a13 minus a23 plus a33. So this is the first column element here. Okay, so this is the first column element, first or second column and first or third column, and the transformation we have applied here is r1 changes to r1 minus r2 plus r3. So this is the transformation we have applied. So we are not applying any transformations on second and third rows, so they remain as it is, a21, a22, a23, a31, a32 and a33. So this is how we get this determinant, and if you see both these determinant values will remain the same. Not only this, even if you apply some more transformation, c2 changes to c2 plus c3, you can apply any number of transformations. So these row transformations or column transformations cannot impact the value of the determinant. Okay, and I would like to give one more point again. 6. If two rows or two columns, if two rows or two columns of a matrix of a determinant, or you can say of a determinant are equal or proportional, you can say, or proportional, then the determinant value is 0. Then the determinant value is 0. Okay, so then the determinant value is 0. Means let us suppose if you have something like this, a11, a12, a13, a21, a22, a23, a21, a22, a23, for example, then in such case if you try to calculate the determinant value, you will definitely end up with a 0 sign. The reason being these two rows are identical actually here. correct? Similarly, if two columns are identical also, then also your determinant is 0. Or sometimes what happen, they can be proportional. Means let us suppose here I have some constant k1 into a21, k2 into a22, or k1 into a21, k1 into a22, k1 into a23. In such cases, what you will do, you will take out the k1 constant, and again these two rows will become same. Okay, so that's how, if two rows or two columns of a matrix are either equal or proportional, then definitely their determinant value is going to be 0. Okay, so this is again one of the very nice properties, because many times we try to bring determinants in such form so that to make them to show that the value of the determinant is 0. Okay, so that's why this is one very important property again. And now seventh, okay, so just a minute. Yeah, so seventh property, determinant of A into B is basically equal to product of the individual determinants, det A into det B. Okay, now I'd like to give, we have talked about a lot of special type of matrices, orthogonal matrix, we have talked about determinants of lower triangular, upper triangular, diagonal matrix. So now let us try to talk about this determinants of this special matrices that I told you, orthogonal matrix, involutory, idempotent, all these cases basically. Okay, so let us see what are the cases. 8, the determinant of a skew-symmetric matrix, the determinant of a skew-symmetric matrix of odd order. What's the meaning of odd order? If you have a matrix of this size n by n, because it's a skew-symmetric, so it has to be square matrix, n is odd. Okay, n is odd basically. So this is a skew-symmetric matrix of odd order, is always 0. Is always 0. How? This property is one really very important property, that determinant of a skew-symmetric matrix of odd order is also 0. Recently in JEE Advanced also you have a question on this basically in this year. So anyhow, let us see how this is happening. Means if you take any skew-symmetric matrix of odd order, third order, fifth order, seventh order, ninth, any order, so that value is always equal to 0. How come? See here. So I would like to give you this analysis here. You can see A is skew-symmetric, correct? So here this A is a skew-symmetric matrix. So A is a skew-symmetric matrix here, correct? So if A is skew-symmetric matrix, then A is equal to minus A transpose, which you know. Now if you apply determinant on both matrices, because both these matrices are same, minus A transpose, so this implies that A is equal to, look, to this A transpose, can I treat this -1 as some scalar multiplication, because k value can be -1 also. So if you treat this -1 as multiplication to this A transpose, so if I want to take this -1 out of this determinant, I know I need to take out this k as k power n times. So let us suppose if the matrix order is of n by n, I can write this as -1 whole power n into that of A transpose. So from this equation, what can we write? Dat A is equal to -1 whole power n into, this property, determinant of A transpose is same as det A. So this is again equal to det A. So from these two equations you can understand one thing. This implies det A minus -1 whole power n times of det A is equal to 0. And this, if you take det A common, you have 1 minus -1 whole power n is equal to 0. This is the equation that you attend with. But now try to observe one thing. Let us suppose if n is even, for example. Okay, if n is even, then what happens? This -1 whole power n gives you an even number, correct? So if n is an even number, -1 whole power n gives you +1, and 1 minus 1 is always 0, and this equation gets satisfied irrespective of this det A being 0 or not, correct? I'm repeating, if this n value is even, then this -1 whole power n will become 1, and this 1 minus 1 product will definitely come out to 0, correct? So even if det A is 0 or non-zero doesn't matter, this equation always holds good when n is even. So that's the reason when n is even you can't comment anything. Now if n is odd, then -1 whole power n is equal to -1, correct? So this implies det A times of 1 minus of -1, which is equal to 2 times of det A is equal to 0, and this gives you det of A is equal to 0. Okay, so this that A is equal to 0 under two conditions. First thing, A is q-symmetric matrix, and more importantly, this n is odd number, correct? So that's why if you take any determinant of q-symmetric matrix of odd order, definitely the answer turns out to be 0. Clear? So many times they ask you, they give you questions like this in exams. The determinant of the value, the determinant of the matrix, the determinant of the matrix, the determinant of the matrix given by, they give this matrix like this: A is equal to Aij for all 1 less than or equal to I comma j less than or equal to 5. It's a 5 by 5 matrix, and Aij is equal to Aij is equal to I square minus j square, for example. Okay, so they have given you some complicated function. I mean, it's not very complicated, but again slightly complicated. So I square minus j square means if you want to calculate third or fourth column element, 3 square minus 4 square is going to be A34, correct? So like this, if you try to frame a matrix, it takes a lot of time to form the matrix. Second thing, it's a 5 by 5 matrix. So even after forming the matrix, the time taken by you to calculate the determinant will be very large. So that's why if you observe one thing carefully, in such cases, Aij is equal to I square minus j square, correct? So if I calculate Aji, what is this? J square minus I square, obviously, correct? So if I pull out a minus sign, this is I square minus j square, which is nothing but minus this I square minus j square I can replace with Aij. So that's why if you see this matrix Aji is equal to minus Aij, this is the notation for this skew symmetric matrix. Okay, so if this is the condition, then this matrix is skew symmetric matrix. So obviously you know that this matrix is a skew symmetric matrix and n value is odd, so definitely this determinant is going to be 0. Okay, so n is equal to 5, which is odd. So therefore you can decide directly that A is equal to 0. Okay, so I'm telling you in general, here it need not be 2, it can be 3, 4, 5, anything, any number, as long as it is of the format I power k minus j power k, definitely it's going to be a skew symmetric matrix because of this 2-3 steps what I have written here. Clear? So that's how the determinant of every odd order skew symmetric matrix is basically 0. Clear? I hope I'm clear till this point. So let's go to the next property, next important property. So the determinant of an orthogonal matrix, the determinant of any orthogonal matrix, you can say the determinant of any orthogonal matrix is plus or minus 1. That's it. Okay, you can never find a orthogonal matrix being singular, which means you can never find any orthogonal matrix whose determinant is 0 basically. Clear? Because orthogonal matrix can take only 2 values for its determinant. One is plus 1, another is minus 1. Okay, let's see how this happens. Look, you have A times A transposed is equal to I, correct? So or A transpose into A is also equal to I. That's one very important thing. So now if you see, if you apply transpose to both sides of this, if you apply determinant to both sides of this equation, this is product of two matrices, so I can write them as individual products. Det A into det of A transpose is equal to, we all know the determinant of identity matrix is 1. So this implies det A into, now determinant of A transpose is same as det A. So this is again det A and this is equal to 1. So det A whole square is equal to 1. So this determinant of A is basically equal to plus or minus 1. So if you find one thing, I've told you in yesterday's class also, normally since you know what is inverse and all, I'll tell you one thing. I told you A inverse is equal to A transpose for this matrix, correct? If you remember, for this orthogonal matrix, A inverse is equal to A transpose. Now for the given orthogonal matrix, you can always have transpose, because transpose is nothing but just interchanging rows and columns. So if A transpose is always present, A inverse is also always present, and you can clearly know from this determinant is never going to be 0. So there is no obstruction for the formation of this A inverse. Clear? And basically I want to tell you one thing. What is orthogonal matrix also I'll tell you basically. So if you take any two rows and any two columns of any orthogonal matrix, for example I have given you this matrix cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. So basically if you take any two rows or two columns, then those two rows and two columns will be perpendicular to each other. What is the meaning of this? Let us suppose if I write this as cos theta I bar plus minus sin theta j bar plus 0 into k bar. Similarly, sin theta I bar plus cos theta into j bar plus 0 into k bar. Means if I take these three rows as three vectors, for example, then if I take any two vectors, then definitely the dot product of these two is going to be 0. You can tie if you want. Look, if I multiply these two rows, for example, cos theta into sin theta cos theta plus minus sin theta into cos theta, this 2 gets cancelled, 0 into 0, 0 again. Similarly, if you take any two rows, 0 into sin theta, 0 into cos theta, 1 into 0, again 0. So dot product of any two vector, rows, if you take by general, this or columns also it can be. For example, you can take first and last column, any two columns. This dot product will always remain 0, which means, and that's the name why this matrix is also called orthogonal, means perpendicularity. If you take any two rows or columns and if you do the dot product of these vectors, definitely you will get 0 here. Clear? So that's why this analysis and this matrix is one very special kind of matrix actually. Clear? Now let us go for some more properties. The determinant of an idempotent matrix is either 0 or 1. Is either 0 or 1 again. How you know this? Again, look, we have seen the definition of idempotent matrix. So a square is equal to I. So if you apply determinant on both sides, det a whole square is equal to I det I. So this det a whole square can be written as, or you can write det a square. This can be written as det a whole square, which is equal to 1. So det a is going to be so we are talking about idempotent, right? Yeah, then this is not I, this is a, because idempotent is a. So if you see, this is det a and this is det a. So if you bring this, det a square minus det a is equal to 0. So this implies if you take det a common, then you have det a minus 1 is equal to 0. So this is a scalar multiplication. So definitely if the term has to be 0, this implies either det a should be 0 or det a minus 1 should be 0, which means det a can take two values which are nothing but either 0 or 1. So it's not always guaranteed that idempotent matrix have an inverse, because probably the idempotent matrix can have a 0 determinant and obviously you may not find the inverse sometimes. Okay, so whereas in case of orthogonal you can always assure there is some inverse existing. Okay, so anyhow this is the case. Now let's talk about involutive also. The determinant of an involutive matrix. The determinant of an involutive matrix is again plus or minus 1. Okay, as you have seen just now. So a square is equal to I. So this implies det of a square is equal to det of I. So this implies det a whole square is equal to this 1, which means det a is equal to plus or minus 1. So this is again one very important result again. Okay, so sometimes they ask you in examination, they'll give you choose the wrong statement, the determinant of an involutive matrix is 0, such sentences they can give you. Okay, so at that time you should know what is involutive, why these things are happening. But trust me, one thing I'm telling you, your university exam maths is much lengthier as compared to gate maths, and gate maths is relatively very simple. Clear? So now let us try to understand this. Fine, these formulas and all are fine, but let us suppose if you multiply two matrices, because next property I'm going to talk about something about determinant of multiplication, something like that. Now try to understand one thing. Let us suppose you're actually multiplying some matrices. Okay, for example, two matrices. Then what actually you're doing? Okay, this means, okay, multiplication wise, you know, this into this you'll multiply, additions, everything, you'll get one matrix. But actually what is that multiplication doing? Okay, so basically these are called transformation of matrices, or you can say this called transformation matrices. Means let us suppose if I have, for example, I'll give you one simple example. Let us suppose you have some plane, for example. Okay, so this is plane, this is plane. Now let us suppose you have a line y is equal to x, which is passing through the origin. Of course, y is equal to x. Y is equal to x. This is x axis. This is minus x. This is y. This is minus y. And let us suppose this is the line y is equal to x. Now let us suppose you have taken a point a comma b, for example here. A comma b. Now let us suppose this point, if this coordinates, if you write as a matrix form a b, for example, a b, let us suppose you have written like this. Now try to understand one thing. You write this as a b, for example, like this, in the vertical space a b, like this you write this point. Now let us suppose if you want to find a matrix which when you multiply to this matrix, let us suppose there is some matrix A, for example. If you multiply this matrix A to this matrix, let us suppose your intention is to find the reflection of this point, to find the reflection about this line y is equal to x. Okay, so you want to find this reflection point, and you know this reflection point is going to be b comma a, for example, because if you take midpoint and all, but product of slopes and all, you will get this point b comma a very easily. Fine. Okay, now what matrix A, when you multiply with this a comma b, will transform this point as a reflection of this given point? Means basically, if you see, if you multiply a matrix A to this, you will definitely get, let us suppose this is size 2 by 2, this is size 2 by 1, you will definitely get 2 by 1 matrix here. This much you know. But what matrix A can make this coordinates a comma b to get swapped? Means b a. So these matrices, this matrix multiplication is actually, in geometric sense, what it's doing, it's basically reflecting the point. Now what is this point, what is this matrix A? Let us try to understand. Okay, let A is equal to, let A is equal to a11, a12, a21, a22. It's a 2D space, so I'm taking 2 by 2. Now if you multiply this matrix with AB, let us multiply a11, a12, a21, a22. This, if you multiply with this matrix AB, you are going to get BA, correct? So let us see what is this elements. So if you multiply A times of a11 plus B times of a12, similarly A times of a21 plus B times of a22, this matrix is going to be BA. Now you know, if two matrices are equal, their corresponding elements must be same. So now if you equate these two elements, this first element with this first element, you can easily understand a11 value is 0 and a12 value is 1. Similarly, if you equate this element with this element, you will come to know a21 is equal to 1 and a22 is equal to 0. So if you form this, if you replace these values in this matrix, you will get A is equal to 0, 1, 1, 0. So basically this is the matrix which can transform this point. Means you can see this point can be transformed as its reflection if this coordinates are multiplied with this particular matrix, which is given by 0, 1, 1, 0. So this is how matrix multiplication is actually transformation of some given matrices with respect to your interest, your point of interest. You see, something I might have done is a reflection about x-axis or something like that, or reflection about y-axis. I could have done anything. Okay, so these coordinates, these matrices decide how these points gets transformed. Similarly, you have you know, in +1 or +2, you might have gone to something called transformation of axis. Okay, so this cos theta minus sin theta cos theta, if you see, if you multiply that matrix to a point, you will get some other values of x comma y. So if you evolve the axis by some theta degrees, then the new coordinates are given by this transformation matrix, cos theta minus sin theta cos theta. You know, you have learned these things. This is the actual meaning of multiplications. Now why I've talked about this? Because again, next property I'm going to talk about this multiplication of matrices. Look, if product of two non-zero matrices, if product of two non-zero matrices, if product of two non-zero matrices A and B is 0, is zero matrix, basically is a null matrix, you can write, is a null matrix, is a null matrix if product of two non-zero matrices A and B is a null matrix, for example, then what happens? Basically, det A is equal to 0 and det B should also be equal to 0. Look, Normally, I'll tell you one thing. Many of you may feel that if A and B are non-zero matrices, but let us suppose if AB is equal to 0. Whenever AB is equal to 0, if you apply determinant on both sides, you know that det A into det B is equal to 0. So, by scalar equation, you may feel that if one of these two, if det A is 0 or if det B is equal to 0, then this equation holds good. But actually, if some case like this happens, then both, you can write, then both should be singular matrices. Both matrices should be singular. Both matrices should be singular. Okay, so this is one very important point. Why? I'll show you now. Okay, because in it we have a previous year gate question also like this. They'll give you det A equal to 0, det B not equal to 0, det A is not equal to 0, det B equal to 0, such options. And our intuition tells that if one of them is 0, that's good enough. But actually both has to be 0. Why? I'll tell you now. Look, we'll delete this. Now see here, why both has to be 0. Look, let det A is equal to 0 and det B not equal to 0, for example. Okay, let us suppose this happened. One of these is 0, so that again A into B we have 0. So this immediately tells you that B inverse exists. B inverse exists. Correct? Means if det A is equal to 0 and det B not equal to 0, then definitely you know B inverse exists. So if you take this AB is equal to 0 and if you multiply with this B inverse, then you will get one thing. This B into B inverse is I, so A into I is equal to 0 matrix, because 0 into something it is 0. This is given, which is A is equal to 0, which is actually wrong as per our assumption that two non-zero matrices. So A and B should be non-zero matrices. But if you feel that det B is not equal to 0, you are trying to understand that A is 0, which is actually contradiction to our intake that both A and B are actually non-zero matrices. So that's why. Similarly, if you take det A not equal to 0 and det B equal to 0, you will find out B equal to 0. Okay. So therefore, both det A and det B should be equal to 0. Okay, so this is one very important property again in determinants basically, because many times they they keep some questions around this for you. So that's the reason why it's one very important property. The product of two non-zero matrices A and B, if it's a zero matrix, then both the matrices should be definitely singular matrices. Okay, both the determinants should be 0. Clear? So please make a note of these things. Very soon when we come to the practice question session or something like that, it will be very helpful for you. Okay, so and majority you may be having some PYQs with you by this time. So once attending this lecture of 4 to 5 hours almost, you can definitely solve almost some 95% of the questions in engineering maths, in linear algebra. Okay, don't worry, remaining 5% I'll solve in the PYQ sessions. Okay, fine. So let us continue here. So I would like to talk about one very important value of one determinant at this moment. Okay, so I'll also give you some technique for writing, okay, the things for writing any 3 by 3 determinant easily. Okay, look, so see here, let us suppose if A is a n by n matrix with determinant as det A, for example. Let us suppose if this is det A, then det of adjoint of A is how much? So many times what they do, they don't give you the actual matrix. If they don't give you actual matrix, then you cannot calculate the adjoint, but they'll ask you about det of adjoint A, and this question is one very famous question in gate domain. So let us see here, if A is a n by n matrix with determinant as det A, then what is the determinant of adjoint of A basically? Look, I'll tell you. We have this equation, that fundamental equation, that A into adjoint of A is equal to det A into I. Correct? You have this equation. Now, if you apply determinant on both sides, det of A into adjoint of A is equal to det of det A times I. Now, try to understand one thing. This is product of two matrices, so I can split it. Det A times det of adjoint A is equal to, Now this det A is again some number. So, and if A is of size n by n, this I is also of size n by n. So if you want to take this det A out as a constant out of this determinant, then since this I is a n by n matrix, this turns out to be det A whole power n times determinant of I. Now one thing, this determinant of I value is actually 1. So you can cancel det A some n minus 1 times, det A power n minus 1. So therefore you can understand one thing, det of adjoint A is how much? Det A whole power n minus 1. So this result is one very important result for GATE examination. Okay, many times you see you'll find a question from this from this actual equation. Okay, sometimes they go one step ahead and they'll put one more adjoint here, adjoint of adjoint here they'll ask. Let us see what is the case. Let B is equal to adjoint A. For example, you have a matrix A, you have calculated its adjoint, so let us consider that matrix as B. Now since this B is also a matrix, we can write B into adjoint B is nothing but det B into I can write this, correct? So if you again simplify, you will get det of adjoint B is equal to det B whole power n minus 1. You will get again the same analysis. If you follow, you will get det of adjoint B is det B whole power n minus 1. Now if you replace B as adjoint A, so this implies det of adjoint A. If you do this, then you will get something like this. Det B is nothing but det of adjoint A, which you have det A whole power n minus 1 here. So det A whole power n minus 1, this whole power n minus 1. Okay, so if you simplify this, you will end up with something like this. Adjoint of adjoint A is equal to det A whole to the power n minus 1 whole square. Okay, so this is how we have this relation. Now try to tell me one thing. Let us suppose if you have taken one adjoint, you got n minus 1 whole to the power 1. For example, you can say when you took two adjoints, here there is 2, n minus 1 whole square came. Now let us suppose if you put one more adjoint, this turns out to be cube. It's a very simple analysis, again like the same thing if you follow. So many times without giving the actual matrix, and even if they give actual matrix, it takes you so much time to calculate this adjoint A. Okay, so that's the reason if you have this determinant of A value, you can easily tell determinant of adjoint A once you know the size of the matrix. Means basically once you know the n value, you can keep going ahead for the determinants of the adjoints. Clear? So these are very much important properties in determinants that I want to talk about at this moment. Okay, so I think I have discussed some 9 to 10 properties of determinants, which is again very good thing. So these determinants are very important basically for your understanding. Okay, so we have seen the determinants of all the types basically here. Clear? Now one thing, fine, so with this we close this second part of this video, which is determinants. Okay, so we have seen what is a determinant. We have seen determinant is nothing but the summation of product of elements of a row or column with the corresponding cofactors. Okay, so we have seen that, and we have seen certain properties of determinants which are very useful in general examples outside. Now let us try to define one the next part of this. So system of equations, correct? So the main process of learning this linear algebra solving is basically to solve simultaneous system of equations. Okay, but to solve this simultaneous system of equations, or whether you can say even before solving, many of you should know like whether if I give you some equations, whether these equations will have a solution or not. Look, for example, if I give you two equations, I'm just explaining. So let us suppose if I give you two equations, 2x plus 4y is equal to some 8, and again x plus 2y is equal to 9. Let us suppose if I give you these two equations, these are two equations for you, that's it. But actually without solving, you can tell whether this equation, okay, if you try to solve, you'll end up with these equations don't have any solution. But normally it's a 2 by 2 case, it's a simple case. But let us suppose if I give you some big case, 4 by 4, 5 by 5, such cases, you should know some techniques, some mathematical checks to understand whether the given system has a solution or not. Okay, so that's how we check that. So for checking that, we will be in need of one very important concept, which is called rank of a matrix. Okay, so this rank of a matrix is one very important concept, and we'll see the complete system of equations deals around with this rank of the matrix. Okay, so let us see how we go ahead here. So let us put a heading, rank of a matrix. rank of a matrix. Rank of a matrix. So what is this rank of a matrix? Okay, so this is one very important concept, and we all should listen carefully here. Okay, so for next 10 minutes, please don't look anywhere, be focused. So rank of a matrix. So a real number, a real positive number, you can say, a real number in general, you can say, R is said to be rank of a matrix, rank of a matrix A m by n. Okay, so this a real number R, smaller, you can say, is said to be rank of a matrix A m by n. Here you need to observe one thing: this matrix need not be a square matrix to talk about rank. Okay, for example, if you want to talk about determinants, then definitely you should have a square matrix. For rectangular matrices, you cannot talk about determinants. But if your idea is to talk about this A m by n, I mean, if your idea is to talk about this rank of a matrix, then your matrix need not be a basically a square matrix. Okay, so now see, a real number R is said to be rank of a matrix A m by n if first point, all the minus of size R plus 1 by R plus 1 and above are zeros. Second, there exists at least one non-zero minor of size R by R. Okay, so what is the meaning of this? Okay, I have written two conditions here. So first of all the minors of size more than R are definitely zeros, and there exists at least one non-zero minor of this matrix A m by n. Now let us see how we practically do this. Okay, look, let us suppose I have taken some example, because examples make you understand better. So let us suppose I have taken some example. So 1 2 3 4, let us suppose I have taken these elements 2 4 6 8, then say 3 5 7 9, let us suppose I have taken. Now try to understand one thing. This is one matrix, this is of size 3 by 4. For example, I have taken some random matrix. Okay, so this is some matrix basically, and it's of size 3 by 4. Now how do I find the rank of the matrix? Okay, so let us check here. So if I want to find the rank of this matrix, first of all I need to see what is the highest non-zero minor that is possible. So minor is basically some determinant, some part of the matrix, correct? So tell me, if this is a 3 by 4 matrix, what is the maximum size determinants I can take out of this matrix? Can I take 4 by 4 because 4 is the highest? No, because there are only 3 rows in this matrix. So highest order that is possible is third order minus. Okay, we have seen this third order minus. So what are the third order minus that you can take out of this matrix? 1 2 3 2 4 6 3 5 7, means basically I have deleted the fourth column. Now I can take one more possible minor. What is that? Let us suppose I am deleting the third column now. 1 2 4 2 4 8 and 3 5 9. Now let us suppose I have one more minor. If I delete the second row, 1 3 4, I mean second column, 1 3 4 2 6 8 and 3 7 9. And let us suppose I am deleting the first column, 2 3 4 4 6 8 5 7 9. So these are the 4 3 by 3 minors that you can form using this 3 by 4 matrix, correct? Now let us suppose if one of these determinants is not equal to 0, for example, let us suppose even 3 are 0 but at least one determinant is non-zero, then we declare the rank of this matrix is 3, because we cannot form 4 by 4 matrices or above, means we cannot form any 4 by 4 determinants or above determinants, and third order determinants are the highest order determinants that we can form. And if you find at least one non-zero minor, then definitely you can declare rank of this matrix is 3. But let us suppose if all these 4 are zeros, now we need to go for next level. So third order we have seen, means 3 by 3 we have seen. Now if all these are zeros, then we'll go for second order minus. Okay, so second order minus. So basically 2 by 2. Okay, so 2 by 2. So now let us try to understand one thing. 2 by 2 minus, but first before going to 2 by 2, let us calculate these minus. So undoubtedly you can see this determinant value is 0. Why? Because first row and second row are proportional to each other, correct? Second row is just 2 times of the first row, so if you take 1 2 out, first row and second row become identical. Same is the case here, 0. Same is the case here also, 0, and same is the case here also, 0. So basically here all the 4 determinants are zeros, so we cannot find any third order minor or this 3 by 3 size minor as non-zero. So then we need to go for second order minus. Again, if you want to write second order minus, you'll get lot of minors here, correct? You can take 1 2 2 4 2 3 4 6 1 3 4 1 3 2 6. Again, you can get lot of minors, but at least there should be one non-zero 2 by 2 minor. So let us suppose I'm taking this minor for example, 4 6 5 7. So if you see this value, this is not equal to 0 because 5 6 are 30, 4 7 are 28. These two are not equal. So you can form any number of 2 by 2 minors, but at least you are pretty much sure that you have at least one non-zero minor of size 2 by 2. So now if you want to declare a rank of this matrix A, rank of A is equal to 2. If you want to declare this, then you should make one thing very clear, that if you take size higher minus, means if you want to declare this 2 as the rank of this matrix A, then you should pretty much sure that all 3 by 3, 4 by 4, 5 by 5 possible, of course, all these things are zeros, and definitely there exists at least one 2 by 2 minor of non-zero value. Okay, this is what I have written actually here. So if you want to declare this number smaller as rank of this matrix, all the minors of size r plus 1 by r plus 1 and above are definitely zeros, and at least you should have one non-zero minor of size this r by r. If you do the r value with the 2, you will understand the next example. That's it. Okay, now so basically checking this. So if you understand one thing, many of you might have had this question by now: how do you know how many 2 by 2 minors you have, and how do you know whether in that 2 by 2 minors you may have a 0 or not? Look, I'll tell you. If you want to form 2 by 2 minors, you will get 3c2 into 4c2. So this is basically 3 into 6. You will have 18 2 by 2 minors totally. Okay, so writing this 18 2 by 2 minors and checking whether they are zeros or not is not very easy here right now. And of course, if the matrix size is of some 6 by 6, 7 by 7 of such kind, then forming 4 by 4 minors, 5 by 5 minors, this is not very very efficient way to check what is the rank of a matrix. So what we have done for this is, you definitely should have some easy procedure or some constructive way to decide what is the rank of a matrix. So now what we have done is, we talked about one thing which is called row echelon form of a matrix. This is one very important part. Row echelon form of a matrix. Now before going for row echelon form, I forgot to tell you one small thing here. Look, what I want to tell you here is, it is denoted by, you can write here, it is denoted as, or it is denoted by, you can say, row of A is equal to R. Okay, so this rank of A is actually denoted with this symbol rho, the common symbol you take for resistivity or density in mechanical and civil. So if you see, this is the symbol that you denote for this rank. So rank of A is denoted with this row of A is equal to R. Okay, so now let us come to this row echelon form. Okay, so let us come to this row echelon form of a matrix. How do we know that basically what is this row echelon form? Let us see. Then we'll see if a matrix is in row echelon form or not. We'll also see how to convert any given matrix into row echelon form. Okay, we'll see these things. Look, a matrix, let me change the color. A matrix capital A m by n is said to be in a row echelon form, if again there are two conditions here. If first condition, number of zeros before the first non-zero element, before the first non-zero element, before the first non-zero element in a row before the first non-zero element in a row basically. So if you take any matrix for example, then in a row if you take, definitely some elements can be zeros and some can be non-zeros. So if you take the first non-zero element that's coming, if you count the number of zeros before that, so this should be more than number of such zeros in its preceding row. Preceding means one above that, in its preceding row. And second thing, number of zeros before the first non-zero element in a row should be more than number of such zeros in its preceding row. And importantly, we can have second thing as 0 rows if any, means let us suppose doing some transformations, if you get any 0 rows for example, then should lie at bottom of the matrix, should lie at the bottom of the matrix, should lie at the bottom of the matrix, should lie at the bottom of the matrix. Means basically, let me show you one example in row echelon form. You will understand that. Okay, so let us suppose if you take this matrix which is in this form, for example 1 2 3 4 5 6 7 8, all zeros for example, let us suppose you have taken. It need not be square matrix also, it can be some other matrix as well, no issue. Now what is the meaning of the first statement that I have written here? This matrix is actually in row echelon form. This is in row echelon form. How? I will tell you. Row echelon form. Row echelon form. Now how actually this 2 points will actually in line with this example that I have given you here. Let us check. So first statement, number of zeros before the first non-zero element in a row should be more than number of such zeros in its preceding row. Look, what is the meaning of this? Let us suppose I have taken third row for example. If I take this third row, then this is the first non-zero element in this row, correct? So this is the first non-zero element and number of zeros before the first non-zero element are 2 in this case. Now this number of zeros before the first non-zero element is 2, so definitely in its preceding row you should have 1 either or 0 elements. So basically here you can see 1. Why I have intentionally kept 1 here? Because if you take the second row, this is the first non-zero element, so here if you have 1 0, here there should be no 0. That's the reason why I have taken like this. So if you take any particular row, then the number of zeros before the first non-zero element should be definitely more than number of such zeros. Such means again, if you take this second row, this is the first non-zero element and these are the zeros before this first non-zero element. So if you see, this number of zeros before the first non-zero element should be definitely more than number of such zeros in its preceding. So for third row, number of zeros should be more than the second row. For second row, number of zeros should be more than the first row, like this. Okay, so this is what I mean. Second point, it's an easy point, you can understand. Zeros means basically if there is any row which is in which all the elements are zeros, they should lie at the bottom of the matrix basically. So if you see, there is one 0 row which is completely 0, so this should lie at the bottom of the matrix actually. Clear? So that's how this matrix is in row echelon form. Okay, now basically, okay, I have given one direct example and I made you understand how a row echelon form of a matrix look like. But let us suppose if I actually give you one matrix, then how you convert that matrix into row echelon form? That's the very important thing. Okay, so that is what next I'm going to discuss, that conversion of a given matrix into row echelon form. This is one very important part that you should know basically here. Okay, so conversion of a given matrix into row echelon form. So how we'll convert? Look, let us suppose I have given you one matrix. Let A is equal to A11, A12, A13, A14, let us take 3 by 4, A21, A22, A23, A24, A31, A32, A33 and A34 for example. So let us suppose this is the matrix. Now how to make this elements make this matrix a into Echelon form? Let us see. First of all, try to make these two elements zeros. Okay, so when you try to make, what are the transformations you will apply? R2 changes to R2 minus A21 by A11 into R1, and R3 changes to R3 minus A31 by A11 times R1. So let us suppose this is the transformation you have to apply. Now if you apply this transformation, then undoubtedly these two elements will become 0 and all these 6 elements will change. Okay, now here you can have one question. Okay sir, we'll do this, but let us suppose if A11 is 0 and these two are not zeros. Okay, if this element is 0 but these two are non-zeros, then how to do this? Look, simple, you can swap those then. Okay, so when you swap, here you will get a non-zero and maybe 1 0 you will get in some cases. Okay, so that's how you actually perform this transformation. Then this matrix gets equivalent to, first row doesn't change, A12, A13, A14, these two turns out to be zeros. Then you have A22 dash, because this value changes after this transformation, A23 dash, A24 dash. Similarly, A32 dash, A33 dash and A34 dash. This is how the matrix changes. Now this matrix is not in Echelon form. Why? Because if this is the first non-zero element, you have 1 0, so definitely here you should have minimum 2 zeros, but you have again only 1 0. So that's the reason we will make this element again 0. How will you make that? Again one more transformation, R3 changes to R3 minus A-32 by A-22 times R2. This is what you can apply. So if you apply this transformation, first and second row remain as it is. So first and second row remain as it is, A11, A12, A13, A14. Then again you can have 0 0, second row remains as it is, A22 dash, A23 dash, A24 dash, and this third row it changes. This 0 minus something into 0, this will be 0. So this is also one more 0 here, and again these two elements will change, A33 double dash, A34 double dash again. So this is how you have a basically Echelon form. Now if you see in this matrix there are no zeros, so there is nothing at the bottom, but here you can see before the first non-zero element there is no 0, before the first non-zero element there is at least 1 0. It should be definitely, because here it's 0, it should be more than 0. Similarly here there are 2. So this is how you convert any given matrix into row echelon form actually. So now if it's of size 3 by 5 or 5 by 5, whatever it is, you can always have this conversion. And anywhere if you are getting this denominator elements as zeros, then just swap those and try to avoid the 0 division. That's it. Okay, so now why we have taken so much pain in converting a given matrix into row echelon form? What is the relation between this row echelon form and rank of a matrix? So if you want to understand this, you will get this connection with this formula. Rank of a matrix A is equal to number of non-zero rows, in row echelon form of A. Row echelon form of A basically here. Okay, so if you take a rank of A, that is basically equal to number of non-zero rows. Okay, so once independent of the size of the given matrix, if you can convert the matrix into row echelon form, then definitely you can identify rank of the matrix very easily. Clear? So that's one common thing again. So that's why we have taken so much of pain in converting the rank of the matrix to by knowing its row echelon form. Now one thing that I would like to tell here, why we have learned this concept of rank, as I told you, to talk about system of equations, correct? So let us, without doing any time, okay, before going for that, I would like to give you some properties of this rank of the matrix which could be helpful for you. So first property, or I can say properties of rank. You can write some 2-3 properties which are good. So first, rank of A m by n will be definitely less than or equal to minimum of m by n, m comma n, correct? So basically we have seen if it's a 3 by 4 matrix, at maximum rank can be 3 or maybe less than that, depending upon the minus being zeros or not. Okay, so out of these two, which is minimum, the rank of this can be at maximum equal to that, or it can be less than that. And similarly, you know, rank of A is always equal to rank of A transpose, because the minus don't change even if you take transposes of them. Okay, so that's the reason. And third, one very good property I would like to give you, rank of A into B will be less than or equal to minimum of rank of A comma rank of this matrix B here. Okay, so that's how, if you do the product of two matrices, rank of A multiplied with B, then this is less than or equal to minimum of rank of A comma rank of B. So this basically are some good important properties, and especially the third property is somewhat not very frequent, but sometimes it's good to know in GATE examination when you're going for matrices. Okay, so that's how we have this three matrices, now three properties. Now let us go to one very important part of this linear algebra, the main core of this system of equations. System of equations. So almost I'm going to spend some 30 minutes of duration on this system of equations. So this is a very important portion that you all should actually put some interest in. Okay, so system of equations, let us see what is this system of equations and how it actually helps you out. Okay, so let us deal with the case of 3 by 3, the equations with the unknowns. Let us start, because 3 by 3 is generally some not very easy, not very difficult also to deal with. Okay, so let the given system of equations be, let us suppose you have three equations with the unknowns. So let me write them. a11 into x plus a12 into y plus a13 times of z is equal to b1. a21 times of x plus a22 times of y plus a23 times of z is equal to b2. a31 times of x plus a32 times of y plus a33 times of z is equal to b3. Okay, so let us suppose these are the three equations with the unknowns. Now your job is, rather than solving, okay, you have the techniques to solve, we have many methods like Gauss elimination, all these things, but right now let us suppose if you want to know whether this system of equations has a solution or not. Okay, so means if you try to solve these equations, will you get a solution? This is what you're interested to know right now. So if you see, this same system of equations can be written as matrices like this. How come? I can write this matrix a11, a12, a13, this is a23, a32, a33. This, if you multiply with this matrix x, y, z is equal to b1, b2, b3. So this is how you can actually write this system of equations into this matrices. How come? Because if you see, this is a size 3 by 3, this is of size 3 by 1, so obviously this product is of size 3 by 1. Now if you check this, if you multiply these two matrices on the left hand side, a11 into x plus a12 into y plus a13 into z, this is what you will get as the first element, first row element. Second row, a21 into x plus a22 into y plus a23 into z. Similarly third one. So if you see, these left hand sides of the equations are nothing but the elements in the matrix multiplication of these two matrices. Okay, so that's how this given system of equations can be converted as a product of basically some matrices. Okay, so this can be written as a into x is equal to b. So this system of equations can be written in terms of some matrix equations. Ax is equal to b, where a is called, this capital A is called coefficient matrix. Coefficient matrix. So why it's called coefficient matrix? Because you see clearly this is basically your A, and this matrix is formed by the coefficients of the variables in these equations. Next, this x is called variable matrix. variable matrix. Okay, so variable matrix, because that this X, capital X, I'm denoting this capital X is basically here the matrix containing all the variables involved in the equations. So this is variable matrix. Similarly, this is B. So if you see, this B is basically a constant matrix. These are the constants on the right hand side. So this is called constant matrix, which many of you have seen, correct? So now people will tell, if you want X, then X is equal to A inverse into B. You have one method. You have Cramer's rule, you have Gauss-Jordan, Gauss elimination. They have n number of methods. Okay, but my job here right now is not to find the solution, but to know whether these equations have a solution or not. Okay, so let us see how we can do this. So Ax is equal to B. Now a system, and you can see carefully here, these equations are non-homogeneous equations. Why? If you take this equation, this is first degree equation, because first degree term, because here you have a power 1, here also you have a power 1, here also you have a power 1. So all these three have power 1, but here the power is not equal to 1. For example, if you write this z power 0 or x power 0 anything, the degree is 0. So all the four terms of this equation don't have a same degree. So that's why this is called non-homogeneous equations. Okay, so let us write for a non-homogeneous system. For a non-homogeneous system, Ax is equal to B. Ax is equal to B. First case, if rank of A is equal to rank of A slash B. We'll see what is this A slash B. This A slash B is called the augmented matrix. Okay, means basically if you write A slash B, augmentation means addition. Okay, so A11, A12, A13, A21, A22, A23, A31, A32 and A33, for example. So if you take this, then B, augmentation, this is called basically augmented matrix. Augmented matrix, for example. So augmentation means addition, means you will add the column B to this matrix. So B1, B2, B3. This is how you will have your augmented matrix. Basically it's a 3 by 4 in this case. Okay, so this is the augmented matrix. So now if you see, if this rank of A is equal to rank of A augmented B is equal to number of unknowns in the equations. Here you have 3 unknowns basically. So number of unknowns, if this happens, then the system has unique solution, means it will have only one solution. Then the system has unique solution. Unique means only one solution. Unique, basically one solution. Unique means basically one solution. Now it could be possibly that case, if rank of A is equal to rank of A augmented B, but this time both these values are less than number of unknowns. Less than number of unknowns, then the system has, I'll take examples of each these 3 cases. Total there are 3 cases. I'll take examples. I'll show you geometrically what is happening when you when these conditions gets hold. Okay, so then the system has infinitely many solutions. Infinitely many solutions. And third, if rank of A is not equal to rank of A augmented B, I'll show you how these 3 cases can come. So if rank of A is not equal to rank of A augmented B, then the system has no solution. Then the system has no solution basically here. Okay, then the system has no solution. How we can have this kind of systems? Basically, when you have a system with only one solution, normally when you solve two equations, you will get some solution. How a system can have infinitely many solutions? How a system can have zero solution? Let us see the cases of each of them and let us try to understand. I hope this is a very long video, so I expect you to be patient, because obviously it's a very short time, and forget 2023, so definitely you need to spend some good time on this mathematics, because straight away 13 marks, and unknowingly or indirectly you can say many other marks will be coming from this engineering math subject. I have taken this first video to be on linear algebra because you'll feel little comfortable, and next video we are going to make on basic calculus. Okay, so anyhow, let us see here, continue. So case 1, let us suppose I give you two equations. Case 1, let us suppose I have given you two equations. For example, 2x minus y is equal to some 7, let us say, and for example some another equation, 3x plus 2y, let us say. So 3x plus 2y is let us suppose again it is 7. Okay, so if you take for example, let me calculate this. Okay, fine. So let us suppose 2x minus y is equal to 7 and 3x plus 2y is equal to 7. Okay, it need not be 7 and 7 here. In this case, it got happened. Okay, now definitely one thing. If you form this, I'm dealing with 2 by 2 because I want to show geometrically also. If I want to take 3 by 3, then I'll need to talk with planes and all, so it will be a little complicated. So right now I am explaining with 2 by 2, so you all will understand. Now let us suppose if you want to write this basically, shall we make the equation simple a bit? Let us make this constant simple a bit. So this is 3, this is 8, let us take for example. Okay, so I just want to make the equation slightly simple, so yeah, this is fine now. So if you see these equations, now let us try to convert these equations into matrices. Okay, so if you see A is equal to coefficient matrix, basically what is the coefficient matrix? 2 minus 1, 3 2, B is 3 8, and of course capital X is xy. Now if you calculate determinant of A, that A is equal to 4 minus of minus 3, which is 7, so which is not equal to 0. So therefore rank of A is equal to 2. That is clear. Now A augmented B is how much? A augmented B is 2 minus 1, 3 2, 3 8. So definitely this is a 2 by 3 matrix. So the maximum second order minor you can take out of this matrix is this second order. So if you write 2 by 2 minus, directly I am writing. So if you write 2 by 2 minus, the first minor will be 2 minus 1, 3 minus 2. So which is 3 plus 2. Okay, so this is plus 2, and obviously this is not equal to 0. So because that's same as the determinant of A, which means one thing you got here is very clear. Rank of A is same as rank of A augmented B, and of course this is equal to 2, and here 2 is nothing but number of unknowns in this equation, correct? So now if you see rank of A and rank of A augmented B, both are same, and of course these two are equal to the number of unknowns in this equation. So therefore the given system has a unique solution. The given system has unique solution. The given system has unique solution. Okay, so the given system has a unique solution basically here. Now try to understand one thing. Given unique solution. Now how do I know that it has unique solution? So basically if you see geometrically, I told you I'll talk about. So these two are the equations, or two linear equations. So if you try to plot them, you will get straight lines, correct? Let us try to plot these straight lines and let us find at how many points they are intersecting. Okay, so because solution mathematically means geometrically the point where the two lines meet each other, correct, or they cut each other. So now if you try to plot these points, this is x, and let us suppose this is y for example. Okay, so this is your y, origin x minus x, y and minus y. Now try to form this line 2x minus y is equal to 3. So if you write this 2x minus y equal to 3, this equation can be written as y equal to 2x plus 3, correct? So if you see basically if you want to plot that line, so let us find the x coordinate. So if you want the point on x axis, if you put y equal to 0, x equal to 3 by 2, so this is the 1 point, this is 1 point, and if you put x equal to 0, y equal to -3. So the line is something like this. So okay, let me change the ink so you can understand better. So this is one line where, okay fine, so this is the equation of the line 2x minus y is equal to 3. And next, if you want to plot the other line, 3x plus 2y is equal to 8, so y is equal to 4 generally when you do this, and x is equal to 8 by 3. So x equal to 8 by 3 and y is equal to 4, means if you take this line, it turns out something like this. So it comes something like this here. So if you see these two lines, these are the equations of 3x plus 2y is equal to 8, and you can clearly find from this matrix analysis, you found that this system of equations will have a unique solution, correct? And of course, if you see the number of points these lines touch or cut each other is only 1 point, so that's how we have a unique solution. We don't know what is the value of that, but right now your job is to identify whether a given system has a solution or not. If you want me to be more colorful, I have a tool. I generally use this in my, I've used this for the first time in my research, but right now I can show you this graphing calculator by Desmos. This is one very good graphing calculator. So let us see the equations. 2x minus y is equal to 3. So let us see. Yeah, 2x minus y is equal to 3. Okay. Oh, I think I have written something. So 2x minus y is equal to 3. So this is first equation. You see, as I have done the first line, this line, yellow line I have done, you can see that yellow line here also, like 2x minus y is equal to 3. So what about the other equation? 3x plus 2y equal to 8. So let us see. 3x plus 2y is equal to 8. 3x plus 2y is equal to 8. Okay, so 3x plus 2y is equal to 8. You have seen some other line coming like this, the blue line. You can see the colors. A red line is for 2x minus y equal to 3. The line that is a red in color. Blue line is for, means this blue color is basically for this blue line. 3x plus 2y is equal to 8. So if you see, these two are intersecting at this point, and of course using this calculator you can just know the solution also. If you dot this point, 2 comma 1 is the solution of this equations. Okay, but right now we are not interested in solving. We are just interested to find how many solutions does this equation have. This is from the geometry, and this is from the, this is from the geometry, and this is from this matrix analysis. Okay, so that's how you can have some system of equations where you actually have the rank of this coefficient matrix is equal to rank of augmented matrix, and that total value is equal to number of unknowns. So in such cases you will have only one solution, and if you try to solve this equation you will get only one solution, which is x equal to 2 and y equal to 1. So this is the first statement that I'm talking about. If this is the case, then the system has unique or one solution. Okay, now let us come about the second case, case 2. Let us talk about case 2. Case 2. Let us suppose I have given you these equations. X plus 2y is equal to 4 and 2x plus 4y is equal to 8. So let us suppose these are the two equations, for example. Okay, and practically you can understand one thing, right? By looking at the equations itself you can understand one thing. Because it's 2 by 2 you can, because it's 2 by 2 you can just tell them by looking, but for some high systems it's not very possible. Okay, so let us see here. X plus 2y is equal to 4 and 2x plus 4y is equal to 8. So let us suppose if you try to solve this using the matrices. So let us write these equations. So A coefficient matrix is basically 1 2 2 4. What about this B constant matrix? 4 8. So A augmented B is how much? A augmented B is equal to 1 2 4 2 4 8. Now let us try to understand one thing. First of all, let us calculate det A. If you calculate det A, 4 minus 4, which is 0. So this det A is actually 0. So 2 by 2 minor of this A became 0. Now you should go for 1 by 1 minus. Okay, so if you go for 1 by 1 minus, what are the 1 by 1 minus? Total you have 4 1 by 1 values here. 1 2 2 4, and obviously all these are non-zeros, so you can say rank of A is equal to 1. How you know that rank of A is equal to 1? Because second order minor is coming out to be 0. So and you cannot have any third order, fourth order. So the only possible is first order. If you take any of these 4 elements, at least you have one of these 4 elements as non-zeros. So that's why rank of A is equal to 1. Now coming to the rank of A augmented B. Rank of A augmented B. So let us suppose if you take, this is of size 2 by 3. So maximum you can take 2 by 2 minus. So if you take 2 by 2 minus of A augmented B. A augmented B, if you take this matrix, and if you take 2 by 2 minus, okay, so 2 by 2 minus. So if you take this 2 by 2 minus, then we have 3 2 by 2 minus. What are they? 1 2 2 4, means deleted the third column, deleted the second column, and deleted the first column. So you will find by strange that all these values are zeros, because 4 minus 4, 8 minus 8, 16 minus 16, all these are zeros. So definitely you should go for 1 by 1 minus followed by, and you see in this 6 elements there is at least one element which is non-zero. So rank of A augmented B is equal to 1. So here you understood one thing, rank of A is 1, rank of A augmented B is also 1, but these two are not equal to the number of unknowns in this equation, correct? So if you simplify this, means if you write it in a organized way, rank of A is equal to rank of A augmented B, but this is less than 2 because number of unknowns is 2. So as per our understanding, the system has infinitely many solutions. The system has infinitely many solutions. And of course, I am explaining you for a 2 by 2 case because geometrically I can draw some lines and explain you. The system has infinitely many solutions. Okay. So the system has infinitely many solutions. Now try to understand carefully here. If I plot them again, this is your x axis, this is your x axis, and this is your y axis, for example. This is your y axis. So origin, oh, I'm sorry. Yeah. Origin x minus x, y and minus y. So if you take these equations, so the first equation x plus 2y is equal to 4. So if you plot that point basically, so at x equal to 0, y is equal to 2, and at y equal to 0, x equal to 4. So which means the line looks something like this. This is the line. So x value should be little high. So let us suppose I am putting some line like this. Okay. So x is more comparatively. So this is the equation of the line, or this is the representation of this line. X plus 2y is equal to 4. Now mathematically, okay, you got infinitely many solutions, but physically how can you have infinite points of intersection? This is possible when the two lines overlap each other, correct? When two lines are overlapping each other, you can understand that at each and every point both these lines touch each other, so they have infinitely many solutions. So if you plot this 2x plus 4y is equal to 8, again you will get along the same line. You will get along the same line. Okay. Okay, so I'm trying to overlap it slowly. Fine. So if you see, I have just shown some difference at least, so that you can understand that this equation is 2x plus 4y is equal to 8. And if you see, all these points are nothing but points of intersection here. This point. So you have lot of infinitely many points. Obviously on a line you have infinitely many points. So all these are infinitely solutions basically. So infinite solutions. Okay, basically if I give you an equation of a line, how to draw the line. Okay, so if you identify this point and these 2 points, you can draw a line connecting those 2 points. Okay, anyhow, I'll show you on Desmos also. X plus 2y is equal to 4. So the first equation, x plus 2y is equal to 4. So x plus 2y is equal to 4. This is the line, you can see the gain line here. And what about the next equation? 2x plus 4y equal to 8. 2x plus 4y is equal to 8. So 2x plus 4y is equal to 8. So this is in purple color. Okay, one is in green, one is in purple, but right now you cannot see the gain line because the purple has overlapped this green one. Okay, so right now you cannot see, you can see this as only one line, but actually there are 2 lines which are involved here. Okay, so that's the reason why if you see these, they have infinitely many points of intersection always. Okay, so you can see all this, at every point there is a point of intersection. Clear? So that's how this system of equations can have infinitely many solutions when this condition holds good. Means rank of the coefficient matrix is same as a rank of this what do you say, adjoint matrix, but at the same time both of them together are less than the number of unknowns in that equations. Okay, so this is one very important step that you need to make a note of. Now let us go for the last case. So basically that's the third case that we are talking about. This is the second case we have discussed. Let us come to the third case, no solution case. No solution case. Okay, so let us see case 3 also. Case 3. Let us see what is this case 3. Now try to understand one thing. Sometimes equations can have no solution also. How? Look, let me again take one example and let us show again. So x plus 2y or x plus 2y is equal to 4, for example, and let us suppose I have taken the equation, same equation with some different constant. 2x plus 4y is equal to 9, let us say. Instead of 8 I have taken 9. Now you can understand one thing. If both lines do not have any solution, that means practically speaking they are parallel to each other. Okay, if you check the slopes, minus of x coefficient by y coefficient, then minus of x coefficient by y coefficient is same for these two lines. So that's why you can have these two lines as parallel lines. Anyhow, let us check the matrix conditions. So A is equal to 1 2 2 4. So A augmented B is equal to 1 2 4 2 4 9. So you can calculate one thing easily. If you take rank of this matrix, if you take determinant of A, this is equal to 0 straight away. 4 minus 4 0. So rank of A is equal to 1. Definitely clear, because if you 2 by 2 minus are zeros, then you will go for the first order minus, and obviously out of all these 4 elements you can see at least there is one element which is non-zero. So rank of A is 1. Now what about the rank of A augmented B? Let us consider. So A augmented B, if you consider 2 by 2 minus of this, 2 by 2 minus, because they are the highest order minus you can consider. So 1 2 2 4, this is 1 minor, 1 4 2 9, this is one more minor, and 2 4 4 9, this is one more minor. Now you can understand this thing, that this determinant is 0, but this determinant is not equal to 0. Similarly this determinant is also not equal to 0. So out of this 3 2 by 2 minus, you have at least one minor which is not equal to 0. So therefore rank of A augmented B is basically 2 in this case, whereas rank of A is only 1 in this case. Okay, so that's how rank of A and rank of A augmented B both are not equal in this case. So this implies rank of A is not equal to rank of A augmented B. So this implies the system has no solution. The system has no solution generally. So what is the meaning of no solution? Both these lines will look parallel actually if you draw them. So if you take x axis and if you take y axis, so origin x minus x, y minus y. So now if you see this 2x, x plus 2y, we have seen previously the line looks something like this. So this is x plus 2y is equal to 4. This is the equation of the line, x plus 2y is equal to 4. And similarly if you take some other line of 2x plus 4y is equal to 9, will be something like this. Okay, so 2x plus 4y is equal to 9. So 2x plus 4y is equal to 9, and if you see these two lines are parallel and you cannot find any point of intersection between them, so mathematically speaking you don't have any solution. Okay, anyhow I'll show these lines on this plot. The only difference is I made this 8 as 9. Okay, so let us see. So now if you see, when I made this 8 as 9, you can find the two lines, and these two lines are parallel lines actually. You cannot find any point of intersection at any point because these are parallel lines. Okay, so that's how it's clear that whenever, and of course this is a 2 by 2 case, so I have explained you with straight lines. If I go for 3 by 3, I need to draw some planes and all, so it looks a little clumsy, so I haven't taken. But the same case holds good for any size matrix, 3 equations with 3 unknowns, 3 equations with 4 unknowns, anything basically. Okay, so now that's how we have cleared this third point also. Third point. Okay, so basically this point, and basically this system is a non-homogeneous system, correct? This is a non-homogeneous system. Now let us suppose you have a homogeneous system, means your all constants b1, b2, b3, all these are zeros. Then let us see what is the case. Okay, and before going for that, I'll tell you one thing. Look, try to understand one thing. In this case you got det A not equal to 0, correct? So try to remember this thing. Whenever if the determinant of the coefficient matrix is non-zero, you always have a unique solution, because if det A is not equal to 0, here also you will get one minor which is equal to det A. Okay, so that's why these two will be definitely equal if det A is non-zero. Okay, so if det A is not equal to 0, then system will have single or unique solution. Okay, but if det A is equal to 0, then the case falls into one of these two things. Okay, then the system may have infinitely many solutions, or the system may have no solution also. It depends on the further analysis. But if det A is not equal to 0, the system will definitely have a unique solution. This point has to be very clear in your mind. Okay, now, and obviously if det A is not equal to 0, your equation x is equal to A inverse b, you can calculate directly. You will get x value. Okay, single solution, you can directly calculate. This is what it happens. Now I'll write one word here which is actually yes, fine. So a system is said to be consistent, or a system of equations, is said to be consistent. A system of equations is said to be consistent if a system of equations is said to be consistent if the system has a solution. If the system has solution, So basically, what's the meaning of this? These solutions can be unique or infinitely many, doesn't matter, but as long as the system has a solution, it's called consistent system. It can be unique solution or it can be infinitely many solutions, but as long as the given system has a solution, we call that system as a consistent system. And for the system to be consistent, det A can be 0 or it cannot be equal to 0 also, like this, depending on these cases. But one thing is very clear: as long as your determinant of A is not equal to 0, the system always has an inverse, and that system will have a unique solution. Clear? Now let us talk about homogeneous system of equations. Okay, so for a homogeneous system of equations, you can write homogeneous system of equations. Homogeneous system of equations means basically your right-handed term, this B matrix, is actually a null matrix, 0. Okay, so whenever the right hand sides of the equations are 0, you can write 0 into x power 1, 0 into y power 1, whatever you want, and all the four terms of the equation was single degree. So that's why this system is called homogeneous system. Whenever this coefficient matrix is, this constant matrix is 0, this implies A into x is equal to 0 is the system. Now try to tell me one thing. Let us suppose if your A is like this: A11, A12, A13, A21, A22, A23, A31, A32, and A33. Why? The equations are A11x plus A12y plus A13 into z is equal to 0. Similarly, the other two equations. Now, if this is a consistent system, now try to tell me one thing. A augmented B will be A11, A12, A13, 0, A21, A22, A23, 0, A31, A32, A33, 0. Okay, so you will have this system. Now try to tell me one thing. If you are interested to calculate a rank of A, okay, it's a 3 by 3 matrix, you will calculate. If you want to calculate a rank of this augmented matrix, how we will calculate? Look, A augmented B is a 3 by 4 matrix. Correct? A augmented B is a 3 by 4 matrix. So basically A11, A12, A13, 0, A21, A22, A23, 0, A31, A32, A33, this is again 0. now if you see, this is of size 3 by 4. If this is of size 3 by 4, the maximum size minus that you can take out of this is third order, correct? So if you take 3 by 3 minus, I'll tell you one thing here, one very important point I want to reveal here. So if you want to take 3 by 3 minus, what are the matrices, what are the determinants you can have? A11, A12, A13. I have deleted the fourth column. So A21, A22, A23, A31, A32 and A33. So this is one determinant. Okay, now if you delete the third column, then you have A11, A12, 0, A21, A22, 0, A31, A32, 0. You have deleted the third column. Next, if you delete the second column, A11, A13, 0, A21, A23, 0, A31, 33, 0. This is one minor, and the last minor, if you delete the first column, A12, A13, 0, A22, A23, 0, A32, A33, 0. So these are the 4 3 by 3 minors. Now the rank being 3 or less than that depends on only one determinant, which is nothing but this determinant. Why? Because this determinant value is 0. You have a complete 0 column. Okay, you have one complete column of zeros. So this determinant is 0, this determinant is also 0, and this determinant is also 0. So your rank being 3 or less than 3 depends upon this det A, correct? Now try to observe one thing. If you take this matrix A, if det A is equal to 0, then this all third order minors will also be 0, because the rank of this augmented matrix depends only and only on this determinant, because all these three are zeros by default. Now tell me one thing, can I say one thing? Here we don't get any case like rank of A not equal to rank of A augmented B, correct? Why? Because this rank of A augmented B depends upon this determinant, which is again depending on det A. So if det A is 0, then rank of A will be something less than 3. Here also this will be something less than 3. If det A is not 0, then rank of A is 3. This is also not 0. A augmented B is also 3. So here we don't have any case like rank of A is not equal to rank of A augmented B. Now if you see this condition, this case is ruled out. Yes or no? Means, oh, I think something happened. Okay, fine. So if you see one thing carefully, in this case of homogeneous system of equations, this third case is not anymore getting valid. Means these two will be always same, but it depends, depending upon the det value, it has unique or infinitely many. But this case cannot happen in case of a homogeneous systems. What is the meaning of that? The system always has solution. Yes or no? So homogeneous systems always has a solution, and the solution is nothing but x equal to 0, y equal to 0 and z equal to 0. If you replace all these coefficients to be zeros, yeah, so if you see this equation, if you replace all these x, y, z values with the zeros, then definitely these equations get satisfied. So in case of homogeneous systems, it's never a case like the system don't have a solution. The system always has a solution, and the solution is x equal to 0, y equal to 0 and z is equal to 0. Okay, so here you can see rank of A will be always equal to rank of A augmented B. That's why, which means you can write always rank of A is equal to rank of A augmented B, which means the system always has a solution. The homogeneous system, you can write better, the homogeneous system has always has a, the homogeneous system always has a solution, always has a solution. Okay, so now if you see this, what is that solution? X is equal to 0, 0, 0, and this solution is called trivial solution. Trivial solution. What is the meaning of trivial? Independent, it is solution always by default. For when you put x equal to 0, y equal to 0 and z is equal to 0, you need not bother about what are the 9 coefficient values, correct? So this solution always acts as a solution for the given homogeneous system of matrices. Okay, and this solution is called trivial solution. Now let us suppose if det A is not equal to 0. For example, if det A is not equal to 0, then what happens? Rank of A will be equal to rank of A augmented B, and that is equal to number of unknowns. Then the system will have unique solution, obviously. So that unique solution is nothing but this solution. Now if the homogeneous system, for the homogeneous system to have a non-trivial solution, to have a non-trivial solution means apart from 0 comma 0, if it want to have some other solution, then definitely rank of A less than n. N is basically number of unknowns. If you see, this implies determinant of A should be definitely 0, correct? Because A is a n by n matrix. If A is n by n matrix and if rank of A has to be less than n, then definitely this determinant has to be 0. And this point is very, very important point for GATE examination, that for the homogeneous system to have a non-trivial solution, the determinant of the coefficient matrix should be 0. Why this is important? Because they give you a question like this. They'll give you 3 homogeneous equations, and out of these 9 coefficients, they don't give one coefficient value, and they'll ask you for a given system to have a non-trivial solution, what is the constant or the unknown value. So basically what you will do, you'll equate the determinant to 0, so you'll have one equation with one unknown, and you will write the solution of this. Clear? So this is how we decide whether the system has a solution or it don't have a solution generally. Clear? So this is basically the talk about system of equations. Almost half an hour we have discussed on system of equations. So normally if you take non-homogeneous systems, depending upon the ranks of A and A augmented B, you decide how many solutions does the set of equations have actually. Clear? So this is one very important part of this linear algebra, and the main crux of this linear algebra is talking about this vectors, or you can say this equations basically here. Clear? I hope you understood this. So with this we close this part 3, which is system of equations, and basically this ranks of the matrices. Okay, now I would like to talk, before going for one last part, which is eigenvalues and eigenvectors, I would like to talk something on linear dependent vectors and linearly independent vectors basically. Okay, so let us talk about that for a while. Okay, now see carefully here. I'll talk about linearly dependent and independent vectors. Linearly dependent and linearly dependent and independent vectors. Linearly dependent and independent vectors. Let us see what are these linearly dependent and independent vectors. Why I am calling vectors? Because normally if you take 3D space, for example, if you are talking in 3-dimensional space, if you want to draw a position vector, for example, let us suppose x, y and z, let us take in this direction, a right-handed coordinate system. So let us suppose if you want to take a point in space, let us suppose this my fingertip is a point in space which I want to talk about. Then if I connect this origin to this fingertip through a vector, then definitely this point has some coordinates in space a, b, c, correct? So 3 coordinates, x coordinate, y coordinate and z coordinate. Now these 3 coordinates can be represented as a matrix x, y, z. That's why we deal generally vectors in matrices. Okay, so now if you see, anyhow, if x1, x2, x3 and so on, xn are n row or column vectors. What is column vectors? Basically these are column matrices. If a matrix has only one column, it's called a column matrix. If a matrix has only one row, it's called a row matrix basically. Okay, so now if x1, x2, x3 and so on, xn are n row or column vectors and k1, k2, k3 and so on, kn are n scalars, then the combination k1 x1 plus k2 x2 plus 𝐂𝐻, 𝑋𝐻 and so on 𝐾𝑛, 𝑋𝑛 is called linear combination of these vectors. Linear combination of vectors. These are called linear combination of vectors. Okay, now you can understand one thing. Basically what is linear? Just we are changing the size, we are not changing any direction. So if you see, this vector is multiplied with this scalar k1 so that the magnitude of this vector changes but the direction doesn't change, correct? Let us suppose if I take this fingertip, this vector, let us suppose if I add 2 times of this vector, the length changes but the magnitude, the direction of the vector doesn't change. Okay, so that's what I'm telling you. This is called linear combination of vectors. Now this combination is said to be linearly dependent or independent depending on a particular equation. I will show you now. Okay, if k1 x1 plus k2 x2 plus k3 x3 and so on kn xn is equal to 0 for k1, k2, k3 and so on kn, not all zeros simultaneously, not all zeros simultaneously, then we say combination is linearly dependent. We say combination is linearly dependent. Combination is linearly dependent. Look, let me explain you with the help of example, you will understand. For example, okay, so now let us suppose I've taken 3 vectors. Example, let us suppose I can take 3 vectors. x1 is equal to say 1 2 3 for example. x2 is equal to something 2 1 4 something like this, anything. x3 for example, let us take x3 is 1 minus 1 1 for example, something like this. Okay, now try to understand one thing. Let us suppose if I had linear combination, some constant into this plus some constant into this plus some constant into this, then k1 x1 plus k2 x2 plus k3 x3, this will become linear combination. Now let us suppose k1 into x1 plus k2 into x2 plus k3 into this is equal to 0. Let us suppose I am writing this equation. So these are some constants which are to be multiplied and these are 3 by 1 matrices. Now when all these are not zeros, when all these things are not zeros, if this equation is getting satisfied, then we say that these vectors are depending on each other. How come? Look, let us suppose if I keep 1, if I keep this value minus 1 and if I keep this value minus 1. Okay, for example, if I keep this value or plus 1, let us suppose I am keeping plus 1, then when k1 k2 k3, these are all not zeros but still this equation is holding good, yes or no? 1 minus 2 minus 1 minus 1 plus 1 0, means basically here this is a matrix, actually the null matrix 0 0 0. Okay, I have written capital O, that's why, if you see, so this is zeros. Similarly, if you take 2 minus 1 1 minus 1 0, 3 minus 4 minus 1 plus 1 0. So here if you see, this combination is getting satisfied when k1 k2 k3 are non-zeros, actually. Clear? So such combinations are called linearly dependent. You know this word dependent very often. Let us suppose if I give you some equation, y is equal to some function in terms of x, then you say that y is depending on x, correct? So that's basically dependency, and here the vectors are linearly multiplied, so that's why this combination is called linear combination. And here if you see, I can write this equation as, look, can I write this equation as 1 into x1 minus 1 into x2 minus x2 plus x3 is equal to 0. So which means, for example, if I write expression for x2, I can write this as x2 is equal to x1 plus x3. Similarly, if I want to write x3, I'll write this as x2 minus x1. Similarly, I can write expression for x1 also as x2 minus x3 like this. So here if you see, you can write these vectors as depending on some other vectors. Okay, this can happen only if these constants are non-zeros. Look, let us suppose if all these constants are zeros, k1, k2, k3 all are zeros, then definitely this equation will get satisfied. But you cannot write any relation like this. You cannot show any dependency of vectors on the other vectors. So that's why this combination is called linear combination with linear dependent vectors. Now I'll ask you one thing you can understand easily. Look, when I write these vectors, if I take these vectors x1, x2, x3 determinant, let us suppose if I take the determinant x1, x2, x3, means basically my intention is to tell you that let x1 is equal to a1, b1, c1, x2 is equal to a2, b2, c2, x3 is equal to a3, b3 and c3. Let us suppose these are the vectors. If x1, x2, x3 are dependent, are linearly dependent, you can say, are linearly dependent. Now tell me one thing. First, determinant of this x1, x2, x3 means basically x1 is one column vector, a1, b1, c1. This is another column vector, a2, b2, c2. This is a3, b3 and c3. This determinant should be definitely equal to 0. Why it should be equal to 0? Because you know that this x2 is nothing but some combination of x1 and x3. Similarly, if you see, if for example, if I write this transformation, column 1 changes to column 1 minus column 2 plus column 3. For example, if I write this combination, c1 changes to c1 minus c2 plus c3, then what you will get here, x1 minus x2 plus x3, which is actually 0 in this case. Okay, so the first column, if you apply this transformation to this determinant, your first column will be 0. So definitely this determinant is 0. So whenever these vectors, I have taken the 3 by 3 case, similarly same thing holds good for 4 by 4, 5 by 5, all these things actually. Okay, so if you see carefully, if certain vectors are linearly dependent, then you have to do make sure that this determinant is always 0. And why this determinant is 0? Because you can see this whenever things are depending linearly, we get such equations. And if you apply the corresponding transformation, means if you apply this c1 changes to c1 minus c2 plus c3, this first column gets out to be 0. So that's called linear combination of vectors, and this case is said to be linearly dependent. Okay, and obviously if we cannot write any such dependency, we will call the case as linearly independent. Okay, so linearly independent, if you write linearly independent, if you write this, a combination, the linear combination k1 x1 plus k2 x2 and so on plus kn xn is said to be linearly independent if k1 x1 plus k2 x2 plus k3 x3 and so on plus kn xn is equal to 0 when k1 equal to k2 is equal to k3 and so on kn is equal to 0. So whenever all these constants are zeros, you cannot write any linear dependency of a vector on other vectors. For example, you cannot say that x3 is equal to x1 minus x2, anything like that. Okay, and why I have told this about linear independency, I want to give one many point here. Number of linearly independent solutions, number of linearly independent solutions of Ax is equal to B is number of unknowns minus number of unknowns minus rank of A, basically here. Okay, so this point is very important. Basically what happens when you get infinitely many solutions, then few solutions will be linearly depending on each other and few will not be depending on each other. Okay, so if you want to find out what are the number of linearly independent solutions, you have a simple formula for that: number of unknowns minus rank of A. I just want to give you this formulation, so it's necessary for me to make you understand what is linearly dependent and what is linearly independent. So I have talked about this linear dependency and independency a bit, for example. Okay, so now we'll go for this last module of this or the last part of this video, which is eigenvalues and eigenvectors, which is again one very most questions asked region in linear algebra. Okay, so we have discussed about this linear dependent and linear independent combinations of vectors. Now let us go to one next and the last most important part, which is eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So let us see what are these eigenvalues and eigenvectors. These are practically very important vectors actually. Now what are these vectors actually? Look, let us try to understand. So normally you see the definition det of A minus lambda is equal to 0, all these things, that's characteristic polynomial. But why this det of A minus lambda I should be equal to 0? This is what you need to understand, means how the characteristic equation is coming out. Okay, so for writing that you should first of all know what is the definition of an eigenvector. Okay, so let us write eigenvector. Eigenvector. So the definition of this eigenvector is basically any column vector x. Basically this x is not equal to 0, means basically it's not a 0 column vector. So any column vector that satisfies the equation Ax is equal to lambda x for some scalar lambda, and basically this lambda is called eigenvalue of this x. Lambda is called eigenvalue of A, and x is called the corresponding eigenvector, the corresponding eigenvector of lambda, Okay, so this is eigenvector of lambda. Now basically if you see this matrix, X is basically one matrix, it's a column matrix. Now what's happening, if you take any matrix and if you transpose on this, means if you are multiplying these two matrices, means if you are applying this A transformation on this X, you see the outcome is again X, correct? So if you write this in vector form like this, for example, you will understand it better. Whenever you are applying any transformation on a vector, the outcome is in the same direction, but magnitude is changing because depending on the lambda is a scalar, so scalar multiplication of a vector will always keep the direction same, correct? So if you see, these x vectors are such special vectors such that when you apply transformation of this A on this vector, then the direction of the vector remains same but only the magnitude changes. Now try to understand one thing. We have this equation Ax is equal to lambda x, correct? So if you simplify this equation, A minus lambda times of I into x is equal to 0 here, correct? So A minus lambda times of I into x is equal to 0. Now tell me one thing, this equation or this is basically system of homogeneous equations, correct? So this is system of homogeneous equation. Okay, so this is system of homogeneous equation. Now try to understand one thing. if this system has to have a non-trivial solution. Of course, when x is 0, then this equation automatically gets satisfied. You have seen in previous case, when ax is equal to 0, whenever this vector is basically 0 vector, then these equations get satisfied automatically. That's called a trivial solution. But we have clearly defined that this x is non-zero. If this x is non-zero, that means, what do I mean? If this x is non-zero, this implies for eigenvectors to exist, for eigenvectors to exist, this system should have non-trivial solution, yes or no? And you know, for a homogeneous system to have a non-trivial solution, determinant of the coefficient matrix, which means this here in this case, so det of lambda a, this determinant of this matrix should be definitely equal to 0, and this is how you get the characteristic equation. And this equation is called basically characteristic equation, and the roots of the characteristic equation, so basically if you see, this is a polynomial in terms of lambda, so if you solve, you'll get the values of lambda. So the roots of the characteristic equation is called, roots of the characteristic equation are called eigenvalues, eigenvalues basically. Okay, so these are called eigenvalues. So basically how you will calculate the eigenvalues of any matrix? You know, you will equate this determinant to 0. But why that determinant is 0? Because this system of equations should have a non-trivial solution. Understood? So that's the reason why this determinant should be equal to 0. So obviously once I give you the square matrix, then what you can do, you can write a minus lambda times of I, you can get the determinant, you equate it to 0, then you will get some polynomial in terms of lambdas, and once you solve that polynomial, you will be getting the values for this eigenvalues. Okay, so basically this is how you calculate the eigenvalues, and how basically we'll discuss some properties, some important properties of eigenvalues here. Okay, so properties of eigenvalues. Properties of eigenvalues. Properties of eigenvalues. Properties of eigenvalues. Look, the first property that I'll give you here is the eigenvalues of lower triangular comma upper triangular comma diagonal matrix, diagonal matrices are the principal diagonal elements of the matrix, are the principal diagonal elements of the matrix, Okay, so this is how we have the result, because obviously it's very, you might know this very well, because if A is upper triangular or lower triangular matrix, then A minus lambda I will also be upper triangular or lower triangular, because this lambda I subtraction will only make changes to the principal diagonal elements, correct? So if the matrix is by default upper triangular or lower triangular, A minus lambda I will also be upper and lower triangulars. So the det is nothing but product of the principal diagonal elements basically. Means if I want to explain you, for example, if I take a diagonal matrix, A minus lambda I will be like this, 5 2 by 2 I'm talking about. So 0 0 0 A 3 3 minus lambda is equal to 0, correct? Example, I'm talking about one example here. So if you see, if you want to calculate the determinant of this matrix, again the product, so this implies A11 minus lambda into A22 minus lambda into A33 minus lambda. This is equal to 0 basically here. Okay, so if that is equal to 0, then obviously you know this is already in factorized form. So if this has to be 0, lambda can be A11 or A22 or A33. So basically these are the things which we have principal diagonal elements of the given matrix. Okay, so this is one very very important property, and this property generally many times you will be using that in examinations. Okay, and second, I would like to give you second property the sum of eigenvalues of a matrix, the sum of eigenvalues of a matrix, the sum of eigenvalues of a matrix is equal to trace of the matrix, trace of matrix. So basically what is trace of a matrix? This is equal to sum of principal diagonal elements, sum of principal diagonal elements, sum of principal diagonal elements basically here. Okay, so this is equal to sum of the principal diagonal elements. Means basically if I want to mention this, sigma I is equal to 1 to n. Let us suppose if you have n by n matrix, then you'll have n eigenvalues. So this is equal to sigma I is equal to 1 to n aii. That's it. Okay, so a11 plus a22 plus a33 and so on ann. Okay, now coming to the third very important property, the product of eigenvalues. The product of eigenvalues of a matrix is equal to, again it's very important and very simple property of course, is equal to the determinant of the matrix, is equal to the determinant of a matrix, is equal to the determinant of a matrix. Okay, means basically if you take the product, notation, product I is equal to 1 to n lambda I, if you take this is nothing but determinant of a actually here. Okay, so these two properties are very much important, and many times you can expect a question from this, that sum of the eigenvalues is actually equal to the sum of the principal diagonal elements, and product of the eigenvalues is equal to the determinant of that particular matrix. Okay, now I'd like to give you some more good information. The eigenvalues of A and A transpose, are same, because you see this means basically if you take this eigenvalues of A and A transpose, if you see the diagonal elements remain the same, and of course the determinant, basically determinant of A minus lambda or A transpose minus lambda I, that remains same. Okay, so that's how the characteristic polynomial is same, and eigenvalues will also be same. Okay, now 5, if lambda 1, lambda 2, lambda 3 and so on, lambda n are eigenvalues of A, then first point, you have certain points here. So first point, eigenvalues of A power m are lambda 1 power m, lambda 2 power m, lambda 3 power m and so on, lambda n power and so on. This result will basically go on and so on, lambda n power m. Okay, so when you raise the power of a matrix, then automatically the eigenvalues also raise their power. And second, so when m value is equal to -1, one special case of A inverse, when eigenvalues of A inverse are 1 by lambda 1, because lambda 1 whole power -1 gives you 1 by lambda 1, 1 by lambda 2, 1 by lambda 3 and so on. This goes on to 1 by lambda n. Okay, so here you can observe one thing. Let us suppose if matrix is singular, means let us suppose if the determinant doesn't exist. If matrix is singular, that means definitely at least one eigenvalue would have been definitely 0, correct? Because you see determinant is nothing but product of the eigenvalues. So if determinant is 0, definitely one of the eigenvalues should be definitely 0. So that's how here if you are writing A inverse, that means you are very much sure that no eigenvalue is 0. So they all are in the denominators. Okay, so no issues. Next, third, eigenvalues of some constant k1 into A plus some B, some k2 into I. Let us suppose if you have some combination k1 into A and k2 into I are k1 times of lambda 1 plus k2, comma k1 times of lambda 2 plus k2, comma and so on, k1 lambda n plus k2. This is how you have the eigenvalues of some advanced terms basically here. Okay, and A transpose has the same eigenvalues, of course. Okay, next, fourth one, eigenvalues of adjoint A. Eigenvalues of adjoint A are det A by lambda 1. This property is very important. Okay, sometimes they ask you this, lambda 2 det A by lambda 3 and so on, det A by lambda n. Okay, so this property is again very much important property. Generally many times they try to frame a question on this. So eigenvalues of this adjoint A are of this form, det A by lambda 1, det A by lambda 2 and so on. Basically they exist like that. Okay, and so generally these are the things which could be available for you. And now I would like to go for the sixth property, which is again some good property. 0 is definitely an eigenvalue. 0 is definitely an eigenvalue of an odd order skew symmetric matrix. An odd order skew symmetric matrix basically. Okay, so 0 is definitely an eigenvalue of odd order skew symmetric matrix. Means basically if you see, you know that every skew symmetric matrix of odd order has 0 determinant. So if that is 0, definitely one of the eigenvalues should be 0. Okay, so this is one very good statement, because now you know logics of all these things. It's not like you by heart something or you just take it for granted. You know why 0 is definitely an eigenvalue, because for every odd order skew symmetric matrix your determinant should be 0. Clear? Now let us continue. 7. Eigenvalues of skew symmetric matrix, or you can write eigenvalues of real symmetric matrix, symmetric matrices. If you take symmetric matrix normally, real symmetric matrices are always real, are always real. Okay, next, 8th property I could give you something like eigenvalues of eigenvalues of skew symmetric matrices. If you talk about skew symmetric, eigenvalues of skew symmetric matrix are either 0, either they will be zeros in case of odd order, or purely imaginary. What is the meaning of purely imaginary? If you take any complex number, basically complex numbers are of this form, z is equal to x plus iy. If you take this as the complex number, then x is called the real part, y is called the imaginary part. So here in these cases this x value will be 0. Okay, you'll have only the y part. So your complex numbers come out in the form like I into some constant basically. Okay, so that's how you have this eigenvalues of skew symmetric matrix. One important property I give you here. 9. Eigenvalues of you say eigenvalues of for example we can talk about orthogonal matrix. Eigenvalues of orthogonal matrix are of unit modulus, means basically what's the meaning of that? If they are real numbers, they'll be either plus or minus 1. If they are complex numbers, then they turn out to be some complex numbers of magnitude 1. Okay, means basically if you calculate root of x square plus y square, that x square plus y square will be 1 actually here. Okay, now there are many more properties actually, but at the gate level these are properties which they generally ask you. But coming to some advanced levels, linear algebra is a fantastic subject, and I would like to give and thank actually one person right now, because by this time you might have passed already 3 hours or 3.5 hours of video, but all this knowledge what I've got is from one person, Gilbert Strang. He has a very good book on linear algebra by Gilbert Strang. He is basically from MIT, and he is fantastic professor across the he is known for his works in linear algebra across the world. Okay, so you can also find him on some YouTube or somewhere in MIT openware courses anywhere. So he's really a fantastic guy. Okay, so eigenvalues of orthogonal matrix are of unit modulus basically, and if you keep on, there are certain many other things, like for example every eigenvalue lies within the circle of certain radius of where the radius is defined by some sum of two other elements. Okay, we have certain things like that very importantly, but right now coming to the gate examination level, all these points could be definitely helpful for you. These 4 or 5 points what I've given here, then these points, and finally these 2 points are definitely many questions in eigenvalues comes from these 2, and of course the first one is a direct thing that you can talk of. Okay, so yes, so generally these are the things that they come off. So 10th, okay, so fine, I think we had a lot of enough eigenvalues and how to calculate this eigenvectors. Okay, so how to calculate this eigenvectors, I'll show you shortly, because we'll deal with one very important concept which is called diagonalization of matrices. Okay, because many of you might be writing engineering sciences paper as well, so this diagonalization is one very important concept in matrices. Okay, we'll see what is this diagonalization. Okay, look, so eigenvectors, so if you write properties of eigenvectors, properties of eigenvectors, properties of eigenvectors. Okay, so properties of eigenvectors, so if you see, we'll write one thing, eigenvectors of a and a power m both will be same, are same. Because what is the difference between them? Look, I'll make you understand one thing. Normally eigenvector means ax is equal to lambda x, correct? Now let us suppose if you make this power m, then what happens? Let us suppose if you have a power m, then the eigenvectors corresponding to this a power m will be just lambda power m times of this x. Yes or no? Look, this lambda power m is just a scalar and it don't actually change the things. So that's why this a power m, if you apply transpose on this will again match each other. So that's how you actually have the eigenvectors of a and a power m both same. Second, I would like to give you this. So second is eigenvectors of a and a transpose are, I would like to change the color because this is important, not same. Okay, are not same actually here. And one very good property I would like to give of symmetric matrices, eigenvectors of symmetric matrices, eigenvectors of symmetric matrices are always orthogonal, are always mutually orthogonal, are always mutually orthogonal. Okay, so these matrices are basically mutually orthogonal actually. Okay, and means basically let us suppose for a 3 by 3 matrix, you'll have, for any given eigenvalue you can have any number of eigenvectors, but if you take any 2 eigenvectors corresponding to 2 different values of lambda, then definitely this dot product is going to be 0. Okay, so now let us try to understand this. This eigenvectors of symmetric matrices are always mutually orthogonal. Now I would like to give one very important point here. Number of linear independent eigenvectors, number of linearly independent eigenvectors of a matrix A, for example, is equal to number of distinct eigenvalues of A, number of distinct eigenvalues of A. Means basically, for example, let us suppose if in a 3 by 3 matrix you got only 2 different eigenvalues, one eigenvalue is repeating, then the number of independent eigenvectors is basically 2 in that case. Okay, so number of distinct eigenvalues of A is what you can have here generally. Okay, so basically these are the basic common elements of the syllabus into all the branches in general. They talk with the linear algebra, then come to the rank of the matrix, determinants, eigenvalues, eigenvectors, again one very important topic. Okay, so basically its majority portion is covered in this video for some quite good time, and I hope this video will definitely help you out in answering your gate questions, and basically to develop some knowledge on this linear algebra as well. Okay, so I wish you all a very good luck, and thank you for being patient for almost some 4 hours of time in this lecture, and definitely this is going to be a very good boost up for all your linear algebra. And this is a single short video, so definitely after this, I believe that you definitely would have gained some confidence in this video and in this linear algebra topic. And very soon we'll be coming up with the next topic, which is basic calculus. Thank you all, and I wish you all a very good luck for your preparation. Thank you.